Now it's time to talk about scanning. So what is scanning? This is active reconnaissance. This is where we rattle the doorknobs. This is where we actually interact with targets. We're trying to find targets that are worth our time and trouble. Our objectives will be discover the hosts that are on the network, discover the services they run and the ports they listen on, fingerprint, not just footprint, but fingerprint the operating systems and the services that run on them, identify targets that are worth a vulnerability scan. When you fingerprint something, you're identifying an operating system or a service version by actively engaging the target, not just by looking at traces that were left on the internet. The goal of scanning is to ultimately find vulnerable targets that we can really go after, that we can really exploit. There are many scan types. You could actively scan or passively scan. When you actively scan something, you're actually engaging that target to see how it reacts. In passive scanning, you're just sniffing the traffic as it goes by and gathering information from that sniffed traffic. You could do a discovery scan. What possible devices are out there? You could do a port scan. What services are running on those hosts and what ports are open? Because an open port is a possible target for attack. We could do a vulnerability scan. See if the services that are running actually could be broken into. And there are other scans as well. We could map host names and IP addresses and MAC addresses. We could identify additional protocols on the network. We could look for stealthy alternatives to port scans. We'll talk more about vulnerability scans just a little bit later in this course. Here are common tasks when we scan. Check for live systems. Use ICMP or ARP to do discovery. Check for open ports. We'll scan the IP addresses that we find to see if they have any open ports. Try to evade intrusion detection and firewalls. We'll use proxies or spoofing or fragments or some other mechanism. Perform banner grabbing. Usually when you make a connection to a service, it will give you some kind of greeting or welcome or do something to identify itself. We want to grab that because if we can identify the type, the make and model, or the type of service, that will inform what kinds of tools we can use to attack it. We could scan for vulnerabilities. We could test services and operating systems for vulnerabilities. Draw network diagrams showing logical and physical pathways. And we'll create a report. A pen test report, document everything we find, identify next steps for exploitation. Now let's talk about packet crafting. I remember when I first heard the concept of packet crafting, I thought, what, are we building network packets from scratch? No, it's not like that. We use packet crafting in more advanced scanning techniques. We don't build something from scratch. What we do is we take like a template, a typical IP, ICMP, TCP, UDP packet, and then we manipulate the various fields either in its header or whatever it's carrying, whatever its payload is. So we'll set different flags on or off, or we'll change different things, or we'll make the packets so they overlap and can't be reassembled. We're manipulating existing plain vanilla packets for our own purposes. Then we send the packet or the packets to the target, and we see how the target responds to something unexpected or illegal. Different operating systems will respond in different ways, so we can often identify the OS based on how it responds. So different things we could set would be like in the IP field, the time to live, the don't fragment flag. We could set the TCP starting window size, or the explicit congestion notification flag, or the sequence numbers. Or we could send ICMP echo request and echo reply, and we could pad stuff in it. We could put stuff in it that is not typical. There are many packet crafting tools. The most notable ones would be things like Nmap, or HPing3, or Colasoft, but there are many others. Here's an example of a GUI-based one. You can see that we can just raise or not raise certain TCP headers. We could set a sequence or ACK number or the window size or whether or not this thing has a different port, different source or destination port. We could set the other options like selective ACK or window scaling or set urgent markers. Or we could put data in the thing. We could also just edit some existing hex to modify that. So there are a lot of different things you can do with packet crafting tools. And the whole idea is that you're trying to create a packet that will get a certain reaction out of your target, and from that reaction you'll go, aha, that's a Windows, that's an Ubuntu, that's a this, that's a that. What if you are scanning in IPv6 networks? Now, these have their own challenges. For one thing, and IPv6 is a whole subject in itself for a networking class, but IPv6 addresses are not just 32 bits long, they are 128 bits long. And because the address space is so gigantic, you can't use normal IPv4 type scanning techniques. They're just like too big. So with these huge address spaces, traditional scanning techniques are not going to be feasible. Some scanning tools just flat out don't support IPv6 networks. However, you could gather v6 addresses rather than trying to scan a whole gigantic thing, because you would be scanning basically 64 bits worth of addresses. Forget it. You could just sniff network traffic to find live addresses. You could look in logs. You could look at header lines in email messages. You could look at other publicly available information like news messages. If we do manage to discover and compromise one host in v6, we could just probe the multicast address, meaning all hosts, and then see who responds. That way we can gather additional targets on that particular link. So this is our introduction to scanning. And now, on to the next topic. Let's talk about a good old traditional method for discovering hosts, and that was using ICMP. Remember the good old days where we would just do a ping sweep across a whole subnet? You send out an ICMP echo request to all of the IP addresses within a range, and you see which ones respond back? Well, that's how it was done in the old days. The discovery scan is the first part of a scan. We have to find out which IP addresses are actually live, so then we can try to part scan them. The ping sweep, the old ICMP echo request, was the simplest way to do it. You send out a bunch of pings and see who responds back. Nowadays, we don't do that so much, and the reason why is most hosts, even in an internal network, will have a software firewall up, which means that they won't respond to ICMP. So when we say discovery scans these days, even ping sweep, the term ping sweep, we usually refer to some other form of scan, like an ARP scan, rather than ICMP. At least that's what's going on these days. You could also use specially crafted TCP or UDP packets as well. Here is the ICMP header structure right here. So ICMP, Internet Control Messaging Protocol. It's a layer 3 protocol. It is a direct payload of IP. It has protocol ID of number 1. It has different message types, and the message types may or may not have codes for further information. So here we are, we'll say message type whatever, it's an 8-bit number. If there's a code after that, and then there's an identifier, maybe a sequence number, and data. And depending upon the operating system, the data could be the alphabet, it could be numbers, it could be whatever. And the reason why there's data in there, that's just filler, because IP requires packets to be at least a minimum size, and an ICMP echo request is too small. So you plump it up with a little bit of fluff, a little bit of filler, so it hits at least the minimum size requirement. So this is ICMP, and it's connectionless, meaning that there's no guarantee that you make a connection at all. You just send it, might get a response back, whatever. The nice thing about it is, you see this data field right here? We could pack other stuff in there, including hide messages or some kind of weird payload, but we'll get to that in greater detail later. You need to know these ICMP types. I'm not going to go over every single one. I'm going to go over the ones that are important for the exam and for a hacker. There is echo reply, that's responding to a ping. Then there's destination unreachable, meaning I had to discard this packet because we can't send it to its final destination for a variety of reasons. Can't reach the destination network, can't reach the actual host, don't know the network, don't know the host. It's not allowed administratively. The host won't allow it administratively. The communication isn't allowed administratively, so destination unreachable. Then there's the source quench. This is a congestion control message. So you've got a bunch of stuff coming and a router just says, source quench, you're just overwhelming me, slow down. So that's source quench, and you can see these message types. Echo reply 0, destination unreachable 3, source quench 4. We have a few more here. There's the redirect. We sometimes abuse this. If you have more than one router, more than one default gateway, the second one might say, hey, don't use that guy, use me. And so we can do that maliciously, saying, don't use your real default gateway, use me, the hacker machine. So we can send a redirect with a code, redirect a datagram for the whole network or for a specific host. Then here's the good old ping. And ping is actually an application, not a protocol. Ping uses echo request. So echo, also known as echo request, ICMP message type 8, is sending out a request. I expect a 0 reply back from you. Then there's time exceeded. This packet took too long to be routed. And if the code is 0, it means, hey, it expired in transit. Like maybe it has the time to live field in the IP header has been decremented through all the routers to the point where it hits 0 and it's discarded. When we do ICMP scanning, like I said, this is the easiest protocol to use to scan for live systems. We send an echo request, we hope to get back an echo reply. It's good for locating local devices. On the internet, if they're public facing, they probably respond to ICMP, but firewalls won't. So ICMP is usually blocked by the software firewall on the host, or a packet filtering router, or an edge router, or an edge firewall that is between the attacker, the scanner, and the target network. But we can use ICMP to determine if a firewall is permitting it. Like an ICMP echo would return a type 3 code 13 with destination unreachable administratively prohibited. That means an admin set something. There's a firewall, and the admin isn't allowing the firewall to respond. No, that's really bad administration. That's like bad configuration. But then from there we go, there is a firewall there after all. So this type of message would be returned from a device blocking a port. It would indicate that a firewall is there, but poorly configured, because firewalls should not respond at all. With a ping sweep, although the traditional method was to send ICMP echoes to a whole bunch of hosts, just like going down the line, nowadays we'll do ARP, TCP, or other protocols. And usually with a ping sweep, we'll do it quickly. 192.168.1.1.2.3.4 in a row. Will that set off intrusion detection alarms? Oh yeah, it will. But we're trying to do it quickly to find live hosts, because after that, then we're going to port scan. And after that, we're going to try to fingerprint and see if we can get in. So that's your basic ping sweep. Only a live host is going to reply. You could use the subnet mask to determine the range of addresses. So you could just say, we're going to ping 192.168.1.0/24, meaning all of 192.168.1 from 1 to 255. Actually, from 0 to 255. Although usually we won't ping 0 because that's the subnet address itself. Then the tool will record all the live hosts in a list for further port scanning. There are many, many, many ping sweep tools. Nmap, HPing3, Angry IP Scanner, pretty much all networking tools will have ping sweep capabilities. Here's an example from Angry IP Scanner. So you can see that the greens were getting responses, and it's actually doing more digging in here. After it gets the responses, it sees if there are any ports that are open and tries to fingerprint the service behind the port as well. With ARP, if we're going to ping sweep, so to speak, with ARP, using ARP discovery, we'll send ARP requests or replies to discover the live hosts. See, the thing is, in a LAN, in Ethernet, and in Wi-Fi, which is not Ethernet, but the two dovetail super easily, you have to be able to discover the MAC address, the physical address of a device, and what its mapping is to an IP address before you can send the packet out. So I might have done a DNS lookup to discover the IP address, but until I do an ARP request to find out what its MAC address is, I can't send the packet out the door. So we'll just send a bunch of ARP requests and see who responds. And we'll just go like down the line. Like we'll say, hey, who has, when we say who, we mean which MAC address, has 192.168.294.78. Tell me. How about 79, 80, 81? And then we'll get responses back from MAC addresses, from network cards. There are a number of tools that can do ARP discovery, and MAP can do it, EtherCAT, Metasploit can enable more than just those, and we'll be playing with a number of these as we go along in this course. And there are other discovery techniques as well. You could send TCP, SYN, ACK, or FIN packets to common ports to see how they respond. You could send ICMP timestamps. Now, the timestamp is used by network routers to synchronize system clocks for time and date. We could abuse that and see if we get a response. We could do SCTP init. SCTP is a new layer 4 protocol. It was introduced really by Google, I think. It's for managing sessions. It uses a heartbeat that will tell you if a connection is down. And some versions of Linux and Solaris have already implemented it. You could also start port scanning a host without checking to see if it's up or down. You could also do what we call an IP protocol scan to see if it responds to other types of protocols besides just TCP, UDP, ARP, or ICMP. So this is our look at discovery scans. And now, on to the next. Let's do a little experimenting with ICMP echo and ARP pings and see how they to each other. I have Kali Linux running here, and its IP address for me is 192.168.252.128. I have XP running its firewall, and its IP is 131. I have all of the other VMs running, but they're minimized so they don't clutter the screen, but they will respond. They're on the network. And then on the host PC, I have Wireshark running. Now, if you're going to capture what the VMs are doing from your host PC, you need to capture from the VMware Network Adapter VMnet 8. That is the interface for the NAT network. The host PC actually has an interface. You can see it right here, 192.168.252.1. That's how it speaks to the VMs via the network. I'm going to start Wireshark on my host. I'm just going to double click the VMnet 8 and I'm going to let it run. I'm going to come over to Kali. And what we're going to do is just do a normal ping of XP at .131. Your address is going to be different. So I'm just going to do a normal ping. And then we're going to see what happened under the hood, because that will have implications for different kinds of ARP pings and ICMP echo pings and that sort of thing. So let's just ping 192.168.252.131. Press enter. Now, since XP's firewall is on, of course we're not getting any responses. So at some point I'm going to click back into Kali and press Control-C to stop. We sent 14 packets. 0 were received back, 100% packet loss. Let's go to Wireshark and see what happened. Stop the Wireshark capture. Let me just expand it a bit so we can take a look. Now, some of this activity will be for normal network traffic that's not related to what we were doing. I do see Kali at 128 trying to ping XP at 131. Now you might ask, why was there no ARP request before the echo request? We do see plenty of ARP requests for .2, but none for .131, which is XP. So why not? The only reason why a host would not ARP first to find a MAC address, and this of course is only on Ethernet and Wi-Fi, and if we want to be fair, token ring, the only reason why it wouldn't ARP first is because it already knows the MAC address. Either somebody hard-coded a MAC to IP mapping in its ARP cache, or it has in the last 10 minutes or so already had some kind of communication with that target, so it doesn't need to do a lookup. It can go straight to the business at hand and send the ICMP echo request. Look, no response. And it tried again and again and again and again and again. And at some point, it said, you know what, maybe the MAC address is wrong. So then it sends out an ARP request and says, well, who does have 131? Please tell me. And here's the interesting part. 131 XP sent an ARP reply. Now remember, ARP is a layer 2 protocol. Firewalls, by and large, do not interfere with what goes on at layer 2. They usually start at layer 3, the IP layer, where ICMP and IGMP would be. They start there and go up. So after some unsuccessful echo requests that gave us nothing back, then Kali just said, you know, maybe the MAC address is wrong. And it did an ARP request and got a reply, and it tried pinging again. And at that point we stopped it, and then there was some other activity not related to what we're doing. Okay, so that is what we expect when a firewall is up on a host. Now let's go over to XP and drop the firewall. Let's turn off the firewall. Let's see what happens. And click OK. All right, the IP address is still the same. I'm going to clear the capture right up here, and no saving, I don't care. And I'm going to start it again, double click again. I'm going to go back to Kali, and I'm just going to type clear just to sort of clear the screen here. And I'm going to up arrow, and I'm going to try that ping again. Now we're seeing responses because the firewall has been dropped. Click into Kali, press Control-C to stop. Come over to Wireshark, stop the capture. So if we look here, and there of course is some stuff that doesn't involve us. We see some DHCPs, and we see some NetBIOS name resolution, and some other stuff that is not related to what we're doing. But if we look, we see our first ICMP echo request from Kali to XP. And we see an echo reply. And by the way, Kali is just double checking on that ARP just to make sure it knows for sure the MAC address. But we do get a reply. And we have another request and another reply and another request and another reply. Now, there's a bunch of junk here that we frankly don't care about. So we could go to a Wireshark filter here, and we could say, well, we only want to see the ICMP, and we only want to see it if it's being sent from Kali to whatever the target is. So we could just say ICMP, just ICMP, and ampersand, the IP dot destination equals whatever XP's IP address is. 192.168.252.131. Now this will show us packets that are being sent to XP. Hit enter. Okay, so we can see all the echo requests, all the pings going out. But the nice thing is that it does tell us if there were replies. If there were not replies, then it would say no response. So this is a quick and easy way to see it. This filter shows packets going to XP's IP address, but we could change it. We could change this to ip.addr, which shows echo requests coming in and echo replies going out of XP. Let's try that. Press enter. So we can see ping, reply, ping, reply, etc. Okay, so everything is behaving as we expect. Let's just try something really simple here. Let's try a for loop in the shell, in the Z shell. Let's do a for loop that basically does a ping sweep of the subnet. Let me clear. And you can use, of course, your snippets, and you can paste this in or you can type it in yourself. I'm just going to copy and paste because I am lazy. So let me copy and paste this, and let me just right arrow so I can see it. This is a very plain for loop. The variable is I, and what it's doing is it's saying ping with just one ping, one packet by a count of 192.168.252 dot, and then I. Now what's I? Well, I is going to be from 1 all the way up to 254. In other words, one ping packet starting at 1, then 2, 3, 4, 5, all the way up to 254. If you get a response of some kind, we will pipe grep, meaning we will take the output of this part and send it to the grep command to search for this text, bytes from. So we're weeding out some of the additional response text that is not that important. So just show us bytes from, and then whatever it is that we got, whatever the IP address is, and then we're all done. Okay, so let's, this time, just restart Wireshark. I'm going to get rid of our filter right now. Let's restart Wireshark. We're not going to save anything. Let's go back to Kali. Let's ping sweep the whole subnet. Now remember, I have actually all of my VMs running. I've got them minimized just to not take up any space on this screen. They will respond, though they are on the network. So let's go. Simple for loop to ping sweep using ICMP echo, using ping, not rping, to ping the whole subnet. Go. And it went through very, very quickly. And you can see the bytes from was parsed out, and then we put in the IP address. Okay, great. Let's stop Wireshark, and let's take a look at what we have. So the question now is, why is there all this ARPing when we did clearly an ICMP echo request? And I want you to think about this for a moment, because if you're going to be a hacker and you're going to look at responses and you're trying creatively to figure out how to break into that target, you need to understand what's going on with the network. This is why having a good background in networking, or having completed Network Plus class and understanding it well, is a really good prerequisite to being a good hacker. So I'm going to go up to the top here, and I can see that Kali is just kind of going down the list. Who has .2, .3, .4, 5, 6, 7, 8, all the way down. It's just sequentially going there. And then it goes to 2. I don't know why it did 2 out of sequence, whatever, but it's like all of these are in the sequence. It has gone down the line, ARPing, all the way up to 127. Kali is 128, so it doesn't bother to ARP for itself. It gets to 129. There's no ARP request for 129. It immediately does an ICMP echo request. It immediately pings 129 without ARPing. Why? The most likely conclusion is that it already has the MAC address from some previous activity, still has it in its ARP cache. It doesn't think it needs to ARP again. It just goes right to pinging, and it gets a reply back. Then it tries to ping 130, and 131. Now, if I look down here a little bit, 131 does respond. Why does 128 try to do an ARP for 131? You might recall that 131 is XP. Why does it ARP for it? Didn't we have the firewall up for XP? Did we? Let's go take a look. Going to go over to XP. Do you remember? Open this up. Now, remember how we dropped the firewall? So it's off. So it does an echo request, and then it goes, you know what? Just in case my MAC address for 131 is wrong, I'll just do a real quick ARP. Hey, 131, what is your MAC address anyway? Or rather, hey, who owns 131? And it gets a reply. And by the way, 131 responds, XP responds because its firewall is dropped. If this is confusing to the eyeballs, let's use our filter. I am going to put in this filter here. Show me any ICMP where the destination is not Kali. In other words, whoever pinging anybody but Kali, which kind of implies that Kali is pinging everybody else. Let's see what responses we get. Okay, good. So here's Kali trying to ping 1, then 2, then 129, 130, 131, 40, and up to 254. And look, what I love about this is no response. So the host virtual adapter .1, although it responds to ARP, will not respond to ICMP. 2, however, which is the default gateway, the VMware default gateway, does respond. 129 responded, 130 responded, 131, 134, but 254, which is the VMware DHCP server, did not respond. Okay, so we have seen how ICMP behaves, and we see that even if you're going to ping using ICMP echo request, you still have to ARP, because that's just how Ethernet and also, quite frankly, Wi-Fi works. They use MAC addresses. You got to have the MAC address before you can send the packet out the door. We've played around with ICMP ping scans. We've seen how ICMP depends on ARP before it can even start. Now let's turn our attention to ARP scans. This SP means no port scan. This TAC cap P cap R means ARP ping. Not a TCP ping, not an echo request, an ARP ping. Let's go over to Wireshark and start a new capture. Let's see what happens. All right, here we go. What is the pseudo password for Kali? It is K-A-L-I, Kali. All right, it went through and found them. Let's stop the capture. Oh, and I need to get rid of this filter. That's why we don't see anything. It did the capture. It's just the filter is in the way. Okay. So there's a bunch of stuff here that is not related to what we want. And if you look for ICMP, just ICMP, just like that, press enter. There's no ICMP. Why? Because this is an ARP ping, not an ICMP ping. Okay, let's clear the filter out. And in fact, what we'll do is let's make sure that the one of the Ethernet addresses is Kali, whether it's source or destination. Let's weed out all the other junk of other machines talking to other machines. Let's say Ethernet eth.addr, and then we'll need to plug in Kali's Ethernet address, its MAC address. So let's switch over, type ifconfig. Here's Ethernet 0. Here's the Ethernet address, the MAC address. So let's just copy this so we can plug it in. Copy the selection, then go back over here and paste it in. Can't have any spaces, so let's get rid of that space. Whether it's source or destination, it's got to involve Kali. Here we go, enter. All right, so now we can see Kali Linux going ARPing down the road, saying, hey, who's 1? Tell Kali. No response. Who's 2? Tell me. Who's 3, 4, 5, 6, 7, 8, blah, blah, blah. Now, the question then is, are there any repeats? I'm scrolling down here, and it's just going up the whole subnet. Does it repeat? Well, it looks like it does. So now we're going to do this. We're going to click info so that it resorts everything. And now we can see that it's doing two of them. One, this is kind of the weird part. One is just the ARP to find out, and the other one then is the ARP scan. So we've got just like a normal ARP, and then we've got the ARP scan, which is why we see two of these. Is there any ICMP in here at all? Let's just clear this filter. Get rid of this filter. Any ICMP? I believe we said the answer was no. No, okay. So that is what an ARP ping will look like. Now, what if you wanted to use Nmap to do an ICMP echo request of a subnet? In other words, scan it just using ICMP, kind of like what we did with the for loop. Well, we can do that too. But there's something special we have to do. So I'm going to copy this next little part. I'm going to clear this out. I'm going to start a new packet capture. I'm going to come over to Kali. I'm going to clear Kali's screen. I'm going to right click and paste. Clipboard or selection, both usually, either one usually works. So, this means absolutely no ARP pinging. This means just ping. Do not also do a port scan. This one means when you ping, do it with an echo request. So no ARP pinging, which is the default in Nmap, to try to ARP ping first, assuming that the connection is on the same subnet. No port scanning. I'm not interested in port scanning. Just echo requests. Ready? Here we go. Enter. And it goes along. Might take a moment. Okay, we have some responses. Let's go over and stop the capture. Why were there all of these ARPs when we told it explicitly? When we said explicitly, no ARP pinging. Just echo request. I want you to answer the question. Knowing what you know, why do we still see all this ARP? Why do we see it? Now, as I scroll up and down, if I go to the protocol, I see some ARP, there's a little bit of DNS reverse lookups, and there are echo requests and echo replies. I expect to see those. But why are there all these ARPs? Well, we talked about that earlier, didn't we? You gotta ARP in an Ethernet LAN and in a Wi-Fi LAN, WLAN. You have to ARP if you're on the same subnet so that you can even ping somebody. We have all these ARPs, but these are just to find out MAC addresses before we can even get to, now let me sort it for ICMP, before we can get to the business of ICMP. So that's our study of Nmap ARP scans. We did ARP scans, we compared them to ICMP echo requests, and we saw how ARP is required just to do the basic business of networking, even before we have an actual ARP scan. Now let's move on to the next activity. Let's perform a host discovery using a Windows-based GUI tool. I have all 5 of the VMs running. If your host PC only has 8 gigabytes of RAM, consider suspending Kali Linux or turning it off so that you have more resources for these. Kali won't actually show very much in a scan because it deliberately doesn't have network services running. In my case, I have enough resources, so I'm going to try all of them. Come on over to Server 2016, click the little Start window, and go to Angry IP Scanner. Click that. This is very typical of a GUI-based, Windows-based IP scanner. First thing I see here is the range, 192.168.252.0 to 255. My question is this scanning the subnet that all of these VMs are on, or is it scanning some other subnet? By default, it should pick up from the host the subnet that is local. But just to be sure, I'm going to open the command prompt and double check. Click Start, go to command prompt. I've made the font bigger so it's easier to see. Type ipconfig, press enter. Oh yeah, IPv4 address for Ethernet 0, 192.168.252, and then server 2016 is .129. Okay, minimize that. So sure enough, we are scanning the local subnet that all of these guys are on. Let's just click Start and see what happens. Gonna click Start and just let it run. This will take a moment, so I'm going to pause the video and come back when it's finished. All right, we're back. Here's some stats. Took a little over 40 seconds. The entire range was scanned. 254 addresses. We found 7 live hosts, and 2 of them have open ports. Okay, close that. Taking a look at this, it's clear that the blue ones are the ones that are live, and the red ones didn't respond. Now notice I didn't say dead. Just because a host doesn't respond doesn't mean that it's not there. It could have a firewall blocking ICMP. So don't immediately assume that there's nothing here. Looking at the first address, if I double click it, it gives me some basic statistics. Okay, now I happen to know with VMware that .1 is actually the host PC. It's an interface, a VMware interface that the host PC uses to talk to this subnet here, talk to the VMs. .2 is the VMware default gateway that is offered to these hosts. It's actually another IP address put on your host interface, but that's a whole other issue. Scroll down, and you can see that it just goes up in sequence, which would light up an IDS immediately. Because it's so fast and sequential, that pattern is immediately suspicious. But in our case, we didn't really care. Scroll down more. Aha. So we can see some things here. This blue, it did respond starting at 128. You know, VMware, the DHCP service, by default starts giving out addresses at 128. So there's this one. Let's double click it. Okay, we don't know the host name, don't seem to have any ports. Fine. But it did respond. This one here, .129, we scanned ourselves. Server 2016, double click that, and we can see that port 80 was obviously open. Okay, 130, Metasploitable. Open that up, and it spotted port 80. And then 131, took a while. Let's open this up. Okay, we don't know the host name. Wow, it took, well, getting on towards 2 seconds for it to respond to a ping, and I'll comment on that in just a moment. Okay, let's go a little farther. Anything else? Down, up, and finally this one. This .254 is the DHCP server address of VMware. Let's do this scan again, but without seeing all of the non-responsive addresses. Come up to Preferences, this little settings gear icon thing here, and click that, and go to Display. And let's just see the alive hosts, the ones that respond to pings. Let's just click that, and click OK. And start the scan again, and we can discard the old results, yes. Let it run. It will take just as long, so I'm going to pause for a moment and come back. Okay, we're back. We can see that we had the 7 live hosts again. Close that. But we don't see all of the non-responsive stuff. We see the same information, but this is easier on the eyes. As for why 131 took so long to respond, I want to address that in just a second here. I can see that .1 and .254, which are VMware specific. They took a while. Okay, I can buy that. But why did one of the VMs take so long? Well, let's go find out. I suppose we want to find out which one 131 is, but it was unable to give us a host name. I wonder if there was a firewall running on that. Well, I just happened to know when I was setting these things up that 131 is, in my case, Windows XP Pro. Your XP Pro and your whole subnet, of course, will be a different address. Probably be 192.168, but the third octet is highly likely to be something different. I'm going to come over to XP, click that, and I'm going to log on. You might already be logged on. Log in as admin with the password of password lowercase. Going to open a command prompt and just find something out here. Let me just make this so it's easier to see. Gonna ratchet up the font. Okay, ipconfig. So XP is indeed 131. All right, fine. Let's go find out about its firewall. We're going to experiment here. Click Start, go to Control Panel, go to Windows Firewall. Click that. Open it up. By default, XP Service Pack 2 has Windows Firewall on. Let's turn it off for a moment. Click OK. Let's scan again, and let's just scan 131. See if it responds a lot faster. I'm going to come up here and just change the range to 131. It'll only scan XP. Click Start. Yes. And of course, it was very quick. Look at it. It responded in 7 milliseconds. Now the question is, if the firewall was on, why did it respond at all? Why didn't it not respond? Well, let's check something out. Come over to Preferences again in the scanner, and you'll notice the ping method in this drop-down box is Windows ICMP. Most firewalls, by default, will block ICMP, which means in theory, this Windows XP Pro over here should not have even responded. It should have seemed to be a dead IP. Well, there are other options here. You could send UDP datagrams, TCP segments, a combination, Java, up at layer 7. You could also do something that's very popular with scanners, and that is use an ARP scan. An ARP scan doesn't try to use ICMP, it sends ARP messages instead. Now, you can't have a firewall blocking ARP. Firewalls don't do that, because if you block ARP, then you can't talk on the network at all. So they all have to permit ARP, which is a layer 2 protocol, right? But ICMP was selected, not ARP. Here's the thing. Most of these scanners, if it says Windows ICMP, that's what it'll first try. And if that fails, it'll try probably ARP next, which is why after failing at ICMP, it then tried ARP afterwards and had a success. Now, of course, we could just pick ARP and click OK. And let's go over here to the firewall again, and let's turn it back on and click OK. Now, you know, when the firewall's on, ICMP failed and the scanner fell back to ARP, but it took, well, getting on to 2 seconds. Let's turn the firewall back on. If we go straight to ARP and not do ICMP first, which is what we just did with these little settings, we said, we'll do ARP first and not waste time on ICMP. Let's see if we get a similar response here. Start, discard, and see what happens. Yep, look at that, even quicker. So in this case, the ARP scan got past the firewall. So with that, that is our look at using a Windows GUI tool to do host discovery. We're now at the topic that everybody loves, port scans. What is a port scan? Well, it means we have to back up a bit and talk about what is a port. Let's say that you go to register your car and you go into the local, in the US we'd call it Department of Motor Vehicles. You have different windows that offer different services. Want to get your picture taken, go to window 27. Want to renew your driver's license, go to window 3. Want to register your vehicle, go to window 17, whatever it is. Ports are very similar. When you have some kind of server or host that offers services to the network, those services have to be differentiated from other services. Like you could be a file and print server and a web server and an email server and a database server all in one box, all in one IP address. Well, how do you keep separate conversations separate? That's the purpose of a port. A port is just a number. It's a number that identifies a process on a network. It's a 16-bit number, meaning it goes from 0 to 65535. Well-known services such as web server, email server, file and print, they use specific port numbers. Now, there is nothing special about one number over another. It's just an ID. But by convention, we know that certain services will be listening on certain ports. So web servers listen on 80 and 443. Email servers listen on 25 and 110 and 143 and 587 and 468, etc. File and print servers will listen on 139, 445, depends upon the operating system. These are just by convention. There's nothing special about a port number itself. It's just we agree upon it because of historical reasons. There's no technical reason for a particular service to use a particular port number. TCP and UDP, both layer 4 protocols, use port numbers. Technically, ports are a layer 5 mechanism to keep separate conversations separate, but the port numbers for TCP and UDP are embedded in the layer 4 header. So you'll see a TCP header with port something, and there will be a source port and a destination port. UDP does the same thing. Usually, when you have a client machine talking to a server, the server will listen on a well-known port, 80, 25, whatever, what is it? What is the SQL one? Well, I forget off the top of my head. But anyway, the server listens on well-known port numbers. The client will use whatever port number its operating system lets it use at that moment. It's really rather unusual to have client and server port numbers be the same. I mean, it does happen here and there, but usually not at all. So the port number will be embedded in the TCP or UDP header. It indicates the kind of payload that this packet is carrying. Clients and servers will have their own ports in a particular conversation. It's usually not the same port. Now, some services, they do not cling to a port very hard. Some services are only what we call loosely bound to a port. Like, for example, Microsoft Web Server, IIS. It listens on port 80, but at least in some of the older versions of the operating systems, you could sneak in Netcat to kind of cut in front of IIS, and Netcat could be listening on port 80, and it would intercept packets coming to port 80. They'd never make it to the web service running in that server. Instead, Netcat would redirect them somewhere else. So we can use tools like Netcat to cut in front of the loosely bound services to hijack and redirect or steal the packets, and they never make it to the ultimate service. So here are the port types. We've got the well-known. Remember, we go from 0 to 65535, 16-bit number. The well-known ports, 0 to 1023, although 0 is not used. These are reserved by convention for the well-known services. Then you've got the registered ports. A service or an application could ask the operating system for additional ports for a particular purpose. So it can say, hey, I also need a couple more. And the OS will say, okay, you can have this one, this one, this one. So these are on request, on demand by services. Then you've got the dynamic ports, 49152 up to the top. These are for client processes, for browsers and email clients and database clients and file and print clients. The operating system will temporarily assign this port dynamically to the client process. So you might open 5 browsers to go to 5 different websites, and the first browser will be like port 49152, then the next one's 153, 154, 155. And as soon as that process closes, you close the browser or the browser crashes or whatever it does, that port is returned back to the OS for whatever the next client process is. So these are the port types. Let's talk about how clients and servers communicate using ports. Clients and servers each have their own port, and those ports are usually not the same. That's fine. The server listens on the well-known port for incoming connection attempts. The client process will identify itself by its port number, tries to make a connection. The server can accept or reject the connection attempt. Usually the rejection happens because there's nothing listening on that port. So if, as a client, I try to make a connection to port 55, and my server has nothing listening on 55, it'll reject the connection attempt with a TCP reset, if it's a TCP connection. Or you can have a firewall filtering ports or other policies that block the connections. So this is the idea of communicating using the ports. Here's an example with ports now. You need to understand this concept because this is what will make a lot of hacking techniques make sense for you. In this case, I have a client, I have a server. The client has multiple client processes running. A couple of browsers, an FTP client, an email client, an RDP client. The server has multiple servers running. The server services are listening on well-known ports. These are very typical. The client processes borrow a port to identify themselves. They borrow it from their own operating system. So let's say the user opens Firefox, a browser, to connect to the server's web server. The operating system of the client assigns Firefox the temporary port 49152. So the web server sees, here comes 49152 to talk to me. Now, let's pause for a moment here. Is it possible for multiple clients with different IPs to all use 49152? Of course. You know what distinguishes them? The combination of the IP and the port and the protocol. So if I have client 100 using 49152 and client 101 using 49152 and client 102, etc., the web server will not be confused because it takes a port and an IP address and a protocol, TCP or UDP, together to make a connection, what we call a socket. So here we are with the Firefox client using 49152 talking to the web server. And then the user opens another browser. Now, quite honestly, it could be another instance of Firefox, but let's say we open Opera. So the operating system is going to give it an unused port, 49153. And then let's say the user uses Opera to connect to the same web server. That's okay. The web server goes, 2 different clients, same IP, but their ports are different. 2 different clients coming to talk to me. And then the user opens up FileZilla. This is an FTP app, and the operating system gives it, whatever port, 51111. And FileZilla makes a connection to port 21, the FTP server. And then the user opens up the Thunderbird email client, 55678, which then makes a connection to port 25. And then the user opens up the RDP client, 61234, which connects to the RDP server, 3389. Now, do we know what ports the operating system is going to assign to the various client apps? No, we don't. And they won't necessarily be in a smooth order either. You will see like 4912345, and then it'll jump to 49168. There will be jumps and gaps. I can't explain why, it's just whatever the operating system is doing at the moment. So here's an example of multiple client apps, client processes, each using a different port to identify themselves, connecting to the well-known ports of a server. All right, hackers, you need to know common port numbers and the services they belong to. You need to know this. So start memorizing. FTP. Now, FTP actually has two common port numbers, 21 and 20. 21 is for sending commands. 20 is for transferring data. But keep in mind 21. That's how we make the connection to the FTP server. Secure Shell, SSH, 22. Telnet, 23. TCP or UDP, 53 for DNS. If you're a client just doing a DNS lookup, you use UDP 53. If you are a DNS server doing a zone transfer replicating to another server, you use TCP 53. HTTP 80. Kerberos, which is the authentication protocol that is used by Microsoft Active Directory. Microsoft didn't create it, but they borrowed it. Kerberos 88. POP3 110. POP3 is one of the email download clients. I'm going to pull my email down from my mailbox. 111, TCP or UDP, this is the Unix Linux port mapper. It is functionally the equivalent of the Microsoft 135 remote procedure call. 139, this is the legacy port, and when I'm saying ports, I mean TCP, unless I otherwise note it. 139, this is for server message block, the legacy number, and that's server message block is the protocol for file and print services. 143 for IMAP version 4, that's another get your mail from your mailbox protocols. 161 for SNMP. The original description of SNMP was that it could be TCP or UDP 161, but right now only UDP is used. 162 for SNMP traps. A trap is when an SNMP running device sends an alert to an SNMP management system saying, hey, something happened to me. LDAP, the Lightweight Directory Access Protocol 389. LDAP is the search and editing protocol for X500 style directory services, in other words, Active Directory. HTTPS 443. 445, which is Microsoft Directory Services. This is the new, well, it's been around for a very long time, but this is the current authentication protocol used for server message block. And when you make a remote connection to a specific Microsoft machine, you make that connection on 445. And when you send a print job or you upload or download files to the Microsoft File and Print service, the server service, you use 445. 3389. Remote Desktop Protocol, RDP. When we scan for open ports, we are basically sending some kind of packet, TCP or UDP, to an IP address with a destination port in our header, knocking on the door to see if anybody answers on that port. An open port indicates there's a listening service, which might be exploitable. TCP and UDP both respond differently to scans. So let's talk about TCP port scans. This is the most common type. As an attacker, we send a TCP packet to the target, and you'll have different TCP header flags raised. The bit is set to 1, and I'll talk about that in greater detail soon. The response can indicate, yeah, I'm open for business on that port. There is a service there. Or can give us a hint on the operating system version, or can even give us a hint on firewall settings based on reaction. This is the TCP header right here. So we can see that we have source port and destination port, all right? And the reason why you see these bits is because network traffic comes serially. It goes, and so like in these spots here, either the bit will be set to 1 or to 0. And so they all come serially, like this, one after another, bits, one after another. It's a stream. And so depending upon the bits, you can see the source port takes up 16 bits from 0 to 15. The destination port takes up bits 16 to 31, another 16 bits. You don't have to memorize this stuff, but just understanding the structure, because understanding network is your key to being a good hacker. So you have the source port, the destination port, the sequence number, and the acknowledgement number. What TCP does, we're going to talk about the TCP handshake in just a moment. The significance of TCP with the sequence number and the acknowledgement number is, I've got a big file to send you. I am not going to try to push it down the network to you in one piece. I'm going to chop it up into small pieces and send them one at a time, and every piece will have a sequence number so you know if any piece is missing. And I will have to resend the pieces that are missing, so you get them all. So the sequence number is, this is piece number 1, and then the next one is 2 and 3 and 4. The acknowledgement number is, yeah, I got 1, I got 2, I got 3. The mechanism is a little more sophisticated than this, and we'll get to it in just a second. Now, another thing that's really interesting are these flags. You'll see there is fin, sin, reset, push, ACK, urge, and then there's ECE and CWR and NS. The first few flags right here, the urgent, ACK, push, reset, sin, fin, these are the ones that are interesting to us. And we'll talk about why in just a sec. The window size basically tells the receiver, hey, how much can I handle? How much data at one time can I handle as you send back to me? And then we have checksums to see if this thing is corrupt and also where the urgent pointer goes. Here are the important TCP flags important for us. SYN for synchronize, meaning I want to start a session. ACK, acknowledgement, meaning I acknowledge that you sent me something. Reset, we're going to stop this connection. This is what you get if you try to start a handshake to a port that the server's not listening on. You'll get a reset saying, hey, this port's not open for business. Fin, finish, we're done transferring our data. Okay, this is a polite way of tearing it down. Push means just send this thing immediately to the waiting application. And then urgent, which is don't bother putting this in the buffer. Don't bother making this thing stand in line. Send it to the front of the line. So there's urgent and then there's push, which is like super urgent. If we were to look in Wireshark and just capture any old TCP segment, they're not really packets, IP is packets. If we were to capture a TCP segment and peel it open, we would see the flags like this. So you can see this is one with the SYN flag raised, which means this is the beginning of a conversation. I'm trying to talk to you. My client is 4050. You are HTTP 80. I am trying to open a session with you, web server. I have the flag raised. So here's the TCP three-way handshake. It goes SYN, SYN-ACK, ACK. The client, and the client is the one that always initiates the connection. That is the network definition of a client, the one that initiates the connection. The client sends a packet with the SYN flag raised, SYN, and it's sent to a specific port. The receiver, the server, whatever that host is, will send back either a reset, hey, not open for business on this port, or a SYN-ACK, saying, I acknowledge what I got from you, and I too will send you a SYN. And really the purpose of SYN flags is to establish the starting sequence number on both sides. And then the first host sends back a final acknowledgement. So SYN, SYN-ACK, ACK. That is a full three-way TCP handshake. Now we're ready to actually start transferring data, whatever the data is. When we're done, and I've downloaded a file, I've gotten my email, I've gotten your web page, whatever it is, when we're done, we'll do a four-way goodbye handshake. Whoever is ending this, usually the client, will say, Finn, I'm done. And the server or the recipient will send back an ACK. Okay, got it. And then now it's time for the server to say, I'm done too. And the client will say, acknowledge that. So FIN-ACK, FIN-ACK. That's the polite way of ending a TCP session. So let's talk about a TCP SYN scan. This is the most common type of port scan. It is also known as the stealth scan or half open scan. Keep those names in mind. SYN scan, stealth scan, half open scan. Client sends a SYN packet to a particular port on the server. The server says, yeah, SYN-ACK, but then the client says, just kidding, reset. So a SYN scan is, it's almost like ding dong ditch, or it's just like, I'm just kidding, I was just joking. So I'm going to send SYN to your port 1, 2, 3, 4, 5. Port 1 will go SYN-ACK, or reset, hey, I'm not open for business. But if the port does send back a SYN-ACK, the client says, I'm just kidding, I'm not really interested in a connection, bye. So that's a SYN scan. It's a quick way of doing things. And also something you need to know, if you are doing a SYN scan, like say with Nmap from Linux, you need administrator privilege or root privilege to do this. The thing about the SYN scan, the stealth scan, the half open scan, is that we are resetting before we actually finish the three-way handshake. So we're just resetting the connection midstream. It's the client saying, oh, I'm just kidding. So that's why the connection is considered half open. Now, it will set off, you do too many of these, it will set off intrusion detection. So here's an example. Here's the attacker. SYN, and remember, this is to a specific port. If the port's open, the server sends back SYN-ACK, and the attacker says, just kidding, reset. The fact that we got a SYN-ACK back means that port is open. We're not going to waste any more time trying to establish a session. I know you're open. Good. Now we have the TCP connect scan. We actually finish the three-way handshake. It's also known as a full scan or open scan. Some people think full scan means that we're scanning all these ports. No, we're doing a full connection in the scan. That's where we allow the handshake to totally finish. SYN, SYN-ACK, ACK, and then we say goodbye. We complete the three-way handshake. We establish a full connection, then we tear it down with a reset. You don't need to be a super user root to do this on Linux. You can do a regular connect scan just being a normal person. And to intrusion detection, this looks normal because that's what clients do. They set up a three-way handshake. The fact that the client says, oh, I have to hang up now, that's okay. It's the least likely to rouse suspicion because this is normal. So we can see an example here. This is a Wireshark capture where I've got two hosts, 10.0.0.234 and 13.107.21.200. The source, 10.0.0.234, sends a SYN, and then the host or the server sends back a SYN-ACK, and the client sends back an ACK. And then if this were just a scan, we would send a reset after that saying, oh, okay, I got to hang up now, sorry. Now there's another kind of scan called the ACK scan. This is where we're really manipulating TCP packets. We use this to determine if the host is protected by a firewall or some kind of packet filtering. Almost every single TCP segment will have an ACK flag of some kind. Receiving an ACK appears normal. In most cases, especially if you go slowly and out of sequence, you can evade IDS from detecting you. The only TCP packet that will not normally, naturally have an ACK flag raised is the very first SYN in a three-way handshake from that client. So we can use an ACK scan against a packet filtering router to see what's behind it, and we'll be checking that out soon. The attacker sends the ACK packet with some sequence number, whatever, to make it look like we're in the middle of a conversation. We send it to a target. If we get no response at all, that's weird. We should get something. If we get no response at all, that means there's a firewall in the way. If we get a reset, that means the port is closed. What do you mean you're acking me? I'm not open for business on this port. We can also observe the time to live in the IP packet here. We could send thousands of ACKs to different TCP ports. We could analyze the time to live field in those reset packets that we get back. If they are less than 64, that's a boundary here, port's open. If it's greater than 64, port's closed. This is one of those little weird things about networking that just we're taking advantage of. Here's another one. We could look at the size of the window. Now, recall that in TCP, you've got one of those fields is window size. That means how much data in one packet can I handle from you? Well, not one packet, before I have to acknowledge. If we sent thousands of ACKs to different TCP ports, we could look at the window size of the reset. If it's non-zero, then the port is open. If it's zero, then the port is closed. So these are different ways of using a manipulative ACK scan to find out information. Here's an example. I'm going to send an ACK. You send me back a reset. The port is unfiltered. I send you an ACK. I either get an ICMP error or nothing. The port is filtered, meaning a firewall is blocking it. Then you can get really fancy with scanning. You can have what are called inverse flags. Stealthier than a SYN scan. We don't even try to start a TCP connection, nor are we sending these bogus ACKs. We'll use it to discover firewall rules or evade detection by intrusion detection, and we'll raise TCP flags using packet crafting in some weird, unusual, illegal pattern that's not normal for TCP. These could include having a Christmas scan. Now, Christmas, they call it that because they figure this packet's lit up with weird flags. It doesn't mean all flags are up. It means that push, urgent, and fin are up at the same time. Now, that doesn't logically make sense. If this packet is high priority, you are either push or urgent, you're not both. And you certainly aren't trying to end your conversation with the same push. You certainly wouldn't have a fin at the same time. So that's like things that don't logically go together. Or you could send a TCP packet with no flags, a null scan. That too is illegal. Or you could just send fin packets and see what happens. Here's an example from Wireshark. We have the urgent flag, the push flag, and the fin flag all set. That's our Christmas scan. Here's an example here. How do we determine is the port open or closed? Send the Christmas flags to a destination. You get no response at all because it'll be like, what? I don't get this. Port's open. You get a reset. That means the port's closed, because the classic thing is something comes on a port and there ain't nothing listening on that port, you'll get a reset. We're going to take a look at different TCP scans in greater detail soon. Then we have UDP port scans. Now UDP, there's no handshake, there's no starting handshake, there's no ending handshake. So UDP is a different kind of beast. UDP is stateless. I don't even know if you got the packet because there's no acknowledgement, nothing. It's like sending postcards. There's no handshake involved. Don't know. So we have to get a little more clever. You can send a UDP datagram, but you will often not get a response unless you're actually saying something that is meaningful to the service behind that port. If you just send a packet, what we call a UDP datagram, you probably get no response at all. So UDP by itself cannot tell if a host is alive, dead, or filtered. Sometimes, if you send a UDP packet to a closed port, you'll get an ICMP error. Sometimes. So that is a UDP port scan. And that is our look at port scanning. Now, on to the next topic. Let's do a port scan using Angry IP Scanner. I have my VMs running, and I've actually left them in place since the previous activity when we used Angry IP Scanner to do host discovery. I'm on server 2016, and I'm going to start the scanner. Again, it's going to scan the subnet. If we look at the settings, come over here to Preferences, click the little gear, and go to Display. We're just showing the ones that respond to the pings. And remember, we found out that with this particular tool, if ICMP doesn't get a response, it'll try ARP. So that's okay, we'll keep that. Let's go to scanning. Let's just use ARP so we just cut to the chase. And then let's go to ports. Right now, it's only going to scan for web ports or what looks like a web proxy port. 8080 is very commonly used for web proxies. So it's not going to tell us about anything else. And it should be quick. Click OK, and let's just go for it. Click Start. Give it a moment to finish. Scanning is done. We can see that Server 2016 and Metasploitable both have web services running responding to port 80. Neither of them seems to have port 443 running. And you know, we can validate that also. In Server 2016, we'll just check ourselves out, come to a command prompt. I'm just going to type CLS to clear the screen. And I'm going to type netstat techna to show in numerical format the status of all sockets and listening ports. Press Enter, scroll up a bit, and I can see that indeed all IP addresses are listening on port 80. We do not have any addresses listening on 445. So Server 2016 is running HTTP, but not HTTPS. Okay, fine. Come back here to our scanner. We can see that Metasploitable is also listening on a web server. Come over to Metasploitable. I'm going to click into it and just press Enter to get a command prompt again. We can also type netstat techna in Metasploitable because the command works in both Windows and Linux. The only problem, of course, with Metasploitable is that there's no using the mouse to scroll back. So what do? You type netstat techna and then you pipe to more, which means it'll go screen at a time. Press Enter. And stopping right here, if I take a look down here, I am listening on FTP. Okay, where's up? There's 80 right there. It's weird that it's not in any particular order, but there you have it. Okay, so that's good. We'd like to scan more, though. I'm going to press Control-Alt to release my mouse from Metasploitable. Come back over here to the scanner and go to the Preferences. And go to the ports. I want to scan for more than just these. How about, put a comma here, how about we scan for FTP 21 through SSH and Telnet 23. So it would be 21, 22, 23, comma. Okay. What else would be good? How about some of the email ports? POP3 would be port 110. And by the way, folks, you need to know these common ports for the exam. IMAP would be 143. Let's see. Oh, SMTP 25. And any other interesting ones? How about some of the Windows-specific ports, such as 135 for remote procedure call, and maybe the old file and print SMB 139? What else? How about the newer version of the file and print 445, which is also the login port? That's pretty good. Think any of these are listening on RDP 3389? Okay, that's a pretty good start. Why don't we try it? Click OK. Let's scan. Discard the old results, yes. All right, we have some results here. Close. I'm curious as to why 131, which I remember is the IP address from the other activity for XP, curious why it doesn't show anything. I think the answer has to do with the firewall. Let's go take a look at the firewall in XP. Click Start. Let's go to the Control Panel. Let's open up Windows Firewall. The firewall is on. And if we look at exceptions, click that. Only remote assistance, which is a different port from what we've scanned, is going to show up. If we were to allow file and print sharing, then some of those ports would show up. In other words, the firewall is blocking any of the services that XP is running. So the services are running, and those services can use the network, but anyone trying to make a connection to the service, they're going to be denied. Well, let's just go and turn the firewall off and see if we get anything. And click OK here. Come back and run the scan again. All right, we're done. I'm going to expand this a little bit so we can see better. Ooh, looks like Server 2016 has the email ports as well as the web server and the Microsoft ports. Looks like Metasploitable has FTP, SSH, which is 22, and Telnet, and SMTP, and the web server. And why is it running the Microsoft ports? Well, the secret is because this particular Linux box also has the Samba server installed. Samba is their reverse engineering version of the Microsoft file and print services. It's a cute little name, Samba instead of SMB, right? So this thing is acting as a Windows file and print server, which is why these ports are open as well. And we can see that XP Pro is running the Microsoft ports. How about, can we scan for UDP with this tool? Not all of these simple Windows GUI tools allow that. Let's click Preferences. Let's go to Ports. I see port selection, but it looks like TCP. You know, if they don't specifically say UDP, they mean TCP. And display, I don't see anything in the display about UDP. Scanning, we saw that we can scan using a UDP packet, but that's just for host discovery. That's just for pinging, not for port scanning. It looks like this particular tool does not do UDP scans. It just does TCP scans. And if I've made a mistake, I expect you to shout so loud that I can hear you across the internet and I can say, whoops, I need to fix that. With that, we have used a simple GUI-based port scanner. We'll try some more complex scanning in other activities. Let's now take a look at other scan types. Some are pretty commonplace and some are pretty exotic. So let's look at all of them. You'll need to know all of these. For one thing, we could just get information by looking at the header of a packet or whatever we get back from this target. With TCP, if you see a window size that is 32120, then that's probably a Linux device. Something other than that, Cisco, Microsoft, unfortunately, they constantly change, so I can't commit to a number right now. IP, time to live, 64 would be Linux or FreeBSD. If you see the don't fragment bit set, if it's set, then it's not going to be SCO or OpenBSD, two operating system types. They don't use the don't fragment flag. We could also look at type of service, although this would indicate the protocol priority more than the operating system. Taking a look at the IP header. So the very first field will indicate, is this IPv4 or IPv6? There is no such thing as IPv5. There are whole reasons for that, which Take a networking class and you'll find out. Then we can see what's the length of the header itself, the priority and type of service, the total length of this packet. There's also an IP ID number, which we'll get to in just a moment. And there are a few little flags here, but not like TCP flags. There's also the time to live and a fragment offset. The purpose of the fragment offset is one of a router's jobs is if you get a huge packet coming in and you have to move it from one type of transmission media to another, like say Ethernet to dial-up PPP, the maximum transmission unit size might not be the same. Like traditional dial-up PPP was 296 bytes maximum, whereas with Ethernet it's 1500 bytes maximum. A router's job is to fragment the packet so that it can go on the new medium. And the fragment offset describes to the far end destination device how to reassemble these packet fragments back into a normal IP packet. And the offset just says at what point or where in the bytes do you reassemble it. So like the first one starts at the first byte, but the second one might start at byte, 1024 or something, and the third one might start at another byte. And one of the really simple, devious denial of service tricks we could do is to send IP packets with fragments that cannot reassemble. And the host will be like, I'm so confused, I can't put this back together. So anyway, that was one way to abuse fragment offset. We also then, of course, show the source and destination IP and if there are any IP options. So we can see this here. So you can see there's a don't fragment. We're telling a router right here, hey, I want you to discard this rather than fragment it, or do fragment it. Also, what is the time to live? So this particular packet can go through 128 router hops before it's finally discarded. The protocol, the payload that it's carrying is TCP as opposed to UDP or ICMP. And then there's some checksums with the source and destination IP and a little bit more information. So there's your basic IP header. Notice the IP ID right here, and we're going to talk about that and how we abuse that in greater detail in a moment. So we've got the IP ID right here, as well as whether or not the fragment flag is set. So now what's banner grabbing? Well, banner grabbing is a way of fingerprinting an operating system or a service. What we do is we try to talk to that device and we see how it first communicates to us. How does it welcome us? How does it hello to us? So we can determine the OS or the service of the remote system depending upon the banner. Some services will identify themselves. So like if you are communicating with an email server, you'll have an email handshake where the banner, the email server says, I am a blah, blah, blah product version something. Or a web server, the banner will describe itself as well. This should not be mistaken for the home page. This is when the handshake is set up. How do the devices talk to each other before we actually get something that the user cares about? So with banner grabbing, there could be error messages or other information that would give us information. Once we know the version of the OS or the service through its banner, its hello message, its welcome message, we can then research, okay, I happen to know that this is a Microsoft IIS 5.0. Let me do some research on the vulnerabilities of this particular type of device, this particular version of a web server. We can also examine TCP and ICMP messages to identify the operating system. So there are different ways to grab a banner. Active banner grabbing, here's some ways. We could send specially constructed packets to the remote and we'll capture the responses. We compare the responses to a database to determine, okay, this is the fingerprint of a such and such. And the responses from the different OSs will vary because of differences in the TCP/IP stack. Passive banner grabbing would be what error message is included. It could tell us about the type of server, the type of OS, the SSL tools used by that target. Or we could just sniff traffic and get information that way. Or we could look at page extensions in a URL, which might help us figure out the version. Like, if in a URL, I see ASPX, I know that that is Microsoft because only Microsoft uses active server pages. So different utilizations for banner grabbing. There are a lot of tools you can use to grab banners. There are many services like FTP, SSH, HTTP, SMTP, POP, IMAP, DNS, Telnet. All of these are going to have banners of some kind. And we can use a variety of tools. So there's a tool, a simple one called IDServe, which is used to grab the banner of a web server. But it can also identify some other internet servers like SMTP, POP, NOS, and FTP. We could use Netcraft. This is an online site that reports operating systems and web servers and NetBlock owners in a graphical view. We could use Netcat, the Swiss Army knife of hacking tools. It's a command line utility that will read and write data across a network connection, but it can grab banners. We could use Telnet, and we'll play with that. We'll play with Netcat as well and IDServe. This is just a command line utility, and originally Telnet was so we could get a remote command prompt. But Telnet, if you try to connect to some other port, can also grab the banner of that port as well. So these are all banner grabbing tools. Here are some examples. We could say Telnet, some IP address, some port number. Now, what port is Telnet normally? TCP/23. But what if we said Telnet, some IP 25? Now we're trying to get the banner of an email server. Or Telnet, some IP 80. We're now trying to grab the banner of a web server. Or we could use Netcat, NZ-TAC-VV, meaning very verbose mode. Some IP address, some port number. See what we get back. Or here's a command, a bash command, echo. Get, which is doing a get request to some web server, some port, and then just look for grep, just filter out, search for the string server and see what comes back. Or we could use nmap, TAC-SV, some target, port, well, the TAC-P, and then specify a port number. Or we can use a script, the banner grabbing script by nmap. So these are all different ways of grabbing a banner. Here's an example of IDServe, written by a really nice guy, Steve Gibson of Gibson Research Company. He's been around for a long time, and really nice guy to chat with. Anyway, he put this out for free so you can use it to grab the banner and identify a particular server. We can also do something called a list scan. Now, in list scan, you're not actually scanning a thing. You don't ping, you don't do any kind of scan whatsoever. Instead, you're doing reverse DNS lookups. You give a list of IPs or names to the scanner, and if you give names, it'll return the IPs. If you give IPs, it'll do reverse DNS lookups, return the names. So you'll get information about what you're going to scan, but you don't truly scan. You just do a DNS lookup. And then there's a zombie scan. Zombie scans are really interesting. It's also known as a blind scan or idle scan. We use it to map open ports on some target, but we don't produce any evidence that we ever interacted with them. So with a zombie scan, we are actually going to do some spoofing and play around a little bit. We'll force a target to interact with a third-party machine, a third machine, what we call the zombie. We will then query the zombie to see if its IP ID, remember how I showed you the IP ID? See if that incremented, if that went up. Because the IP ID will go up regularly in some kind of communication session with every IP packet. The purpose of the IP ID traditionally was to recover from IP fragmentation, but we're going to abuse that. Here's our zombie scan example. Take a look. There's us, the scanner. There's the zombie. We send a SYN-ACK to the zombie. Of course the zombie's going to say, what are you talking about? It'll send us back a reset. We will look at the IP ID. Remember how I talked about that, the IP ID? That number will keep incrementing. It's in the IP header. All right, we have established the zombie's IP ID. Okay, good. Now, we're going to send a spoofed packet to the real target. We're going to send a SYN to the real target. We're going to pretend that the IP source is the zombie. So the real target will think the zombie's trying to start a handshake. If the port is open, the target will send back a SYN-ACK to the zombie, and the zombie will go, huh? What are you I wasn't trying to start a conversation. It'll send a reset back. But now, its IP ID has just gone up by 1. It's whatever the starting number is, plus 1. Okay, now, the last part of this is us, the scanner. We then send another SYN-ACK to the zombie. And the zombie will send back a reset going, what are you talking about? But at this point, the IP ID is now 1 higher, starting number plus 2. If we see that, we know that the zombie had an interaction with the target on that port. Now, what if the port is closed? Here we send the SYN-ACK, we get the reset, IP ID starts out as whatever it is. Then we send a spoofed SYN flag to the target. The target responds to the zombie saying, reset, I'm not open for business on that port. The zombie, when we SYN-ACK it again, is going to just have IP ID plus 1, not plus 2. So depending upon how much it's gone up, will tell us if the port is open or closed. If it's only gone up by 1, that particular port is closed. If it's gone up by 2, there was successful interaction, that port is open, the port on the target. Of course, we don't care about any ports on the zombie. That's not important. Then there's another really exotic scan called the FTP bounce scan. This abuses a particular FTP command called the port command. You know, in FTP, just like HTTP, there are different commands. Like FTP can have get and put. One of the commands is port. And FTP also uses a special file exchange protocol, FXP. The attacker sends the port command to a server to redirect the data connection to yet a third device, the real target. The target device could be anything the FTP server could reach. It doesn't have to be another FTP server. So it's going to go something like this. We'll use it to anonymously port scan some other system. We have to be able to get into an FTP, or we have to be able to reach an FTP server. The FTP server, in turn, has to be able to reach another server. We're asking the FTP server to send files to another server. Not really, but we're using that command. The returned error message will tell us whether the target port is open or not. We use this to bypass firewalls. I mean, for example, what if we had an FTP server that was in a DMZ, in a demilitarized zone, and that FTP server is capable of talking to internal servers as well as machines on the internet? As a hacker, we can't go all the way to the internal network, but we could hit the FTP server and ask it to try to scan a device on the inside. That's the whole idea of the FTP bounce scan. Most modern FTP servers now have that port command disabled. So here's how it goes. We have an internal trusted zone right here in the blue. Here's us out on internet land, not trusted. Here's the public FTP server. We cannot directly, as an attacker, go straight to the internal target. So instead, we'll try to bounce off of the FTP server, which is public facing. We can also abuse something called Universal Plug and Play, UPnP. This is TCP 1900. It enables devices like PCs and Wi-Fi and mobile devices and printers to automatically discover each other. They can establish connections to share services and data. And for entertainment, it's meant to be used on small residential networks. It is enabled by default on millions and millions of systems. Any UPnP exposed systems that are connected to the internet that have exploitable vulnerabilities then open up all sorts of fun avenues. Potentially, UPnP could expose millions of users to remote attacks. We could steal stuff from them. We could use their network for Bitcoin mining or whatever. The Simple Service Discovery Protocol, SSDP, this is sort of the heart of UPnP. It is used to advertise and discover network services and presence information. It's the basis for universal plug and play. So this SSDP can find out, hey, who's on this network without having to do DHCP, DNS, or any of that stuff. We can do it without any special static configurations. Like I said, it's intended for residential or small office environments. And since, you send things out to small environments, people generally don't lock them down. And now we can take advantage of this. So with SSDP scanning, we would try to discover plug-and-play devices on the network. We can discover vulnerabilities and then maybe launch a buffer overflow, denial of service attack, see if a machine can be exploited. It usually works when the internal machines on that person's network are not firewalled. You can send it over IPv4 or IPv6. You can send it over the internet. So that's our look at other types of scans. And now, on to the next topic. Let's see how we can packet craft. And I have two windows open here in Kali because I'm going to send HPing3 specially crafted packets from one window, and I'm going to do a simple TCP dump so we can watch in real time what happens in the other window. My target is going to be Metasploitable over here, this little guy. And we'll just get his IP address real quick. If we ifconfig, I'm just in Metasploitable. The IP address is 192.168.98.155 right here. And let's go back to Kali. So I'll keep in mind that 155. So let me just start TCP dump in one of the windows here. We're just going to do a simple TCP dump. Now you could just say TCP dump and just press enter, and it will show packets as they happen in real time, but it'll show a bunch of stuff we probably don't care about. So I'm going to Control C to break, and I'm going to just do this again. I'm going to TCP dump. I want to see it in verbose mode. Do not bother to do any name resolution. Show me the contents of the packets. That's the TAC capital X. And I just want to filter in on a destination of the Metasploitable. So the destination would be 192.168.98.155. That's my little target. And the source, only give me from Kali, 192.168.98.160, and don't give me anything else. That's the address of Kali. I can show you that being the address of Kali if I just type ifconfig right here. And if I scroll up, you can see that indeed 192.168.98.160 is the address of Kali. So I just want to focus on these. I don't want any other junk showing up, just so it's not confusing. So let me just press enter. Oh, it looks like I've typed in something wrong. Let's take a look here. What did we do wrong? TCP dump tech v tech n tech cap x. Oh, I have to say the word and. So sorry. Let me up arrow. You have to say something and something. Okay, so I have chosen verbose output with no name resolution. Show me the contents of the packets, which is important to us. The destination is Metasploitable and the source is Kali. Let it go. Okay. Now let's actually do some packet crafting. Like I've said, packet crafting doesn't mean you're creating something from scratch. It means you're taking a common packet, framework, if you will, or common packet structure, and you're setting whatever settings you like, and they can be unusual. So we're now going to type some hping commands. If we want to find out the syntax for hping, we can just say hping3, because that's the version of hping we're up to, -h for help. And you press enter, and you can scroll back and you can see all of the settings, all of the switches, all of the options for hping. We're going to use a few of them. We can see that there are a number of them. The usage is the command, the target, and options. However, I've found that you can kind of rearrange these a bit, like Nmap, and it's tolerant of that. Okay, so let's scroll down, and if you notice we could set TCP flags, we could say the ports, source and destination, we could set like ICMP types and codes, we could set fragments, non-fragments, this is IP, we could spoof IP, we can say it's ICMP, UDP, we're doing scans, we're doing raw IP, the default is it'll be TCP, we can have a count of X amount with a wait interval, make it fast, make it flood, have different kinds of output, have debug. So there's lots of options here, more than we care about probably for this particular demo. Let me just type clear, just to make it a little bit easier to see up here. So let's just do an hping3, and let's scan from port 1 to 200, because the default is TCP, and our target, 192.168.98.155. So let's just do a TCP scan of ports 1 to 200 against Metasploitable. And you can watch them coming in. This is TCP dump here. You can see them actually not coming in, but going out from Kali. Now, we have replies. We have replies from FTP, SSH, Telnet, SMTP, DNS, HTTP, Remote Procedure Call 111, and SMB, NetBIOS. So if we scroll back, we can actually see some of this as it happened here. So like right here, we sent from Kali using just a random source port to Metasploitable port 21. And you can see that we were using TCP, and we didn't actually have any TCP flags raised, and so which means we would expect to get a reset back. When you don't have any flags raised, it'll be like, oh, what reset? So we went through all of these different ports and all the way down the line, and we got from ports 1 to 200, and you can even see here, now we've got some ARP requests at the end here, which we don't care about. You can see here that this was aimed at 111 over here, and this one was aimed at 80, and this one was aimed at 53, and 25, 23 here. So we have just some common ports, and we got a response. All right. So now, and of course we didn't scan for anything higher than 200. So we don't have like 3389, which wouldn't be on a Linux machine anyway. Okay, so we've got that. We did a quick port scan, if you will. Now how about let's do something else? How about let's do a UDP scan? So let's hping3, and let's tac UDP, and let's tac scan. And let's try to do a UDP scan from UDP 1 to 200, if there's anything there, to 192.168.98.155, and let it rip. And so you can see they're coming in here. These are UDPs. So we can see that they're going to different ones, like UDP 199, 198, 200. And let's see the report here. All replies received done, not responding ports. It looks like our target was not responding on any of these UDP ports. So here it tried all these UDP ports and got a whole lot of nothing. So it looks like our target is not listening on or not responding on UDP. Okay, well then why don't we just try doing some more specific things? Let's hping, let me just clear. Let's hping3, and this time let's set the SYN flag with a count of 1 to, say, port 21, and we can set our own source port. That's what the TAC small s is, 5150, my little nod to Van Halen there, and then the destination, or the target, 192.168.98.155, And if you don't specify a particular port, then the default will be 0. But we specified port 21. Let's see what happens. Press enter. And we can see that we sent a SYN flag. We got back a SYN ACK, which is what we expect from a TCP handshake. So if we go back just a little bit here, we can see incoming from Kali, going over to port 21. You can see that 21 right there. The SYN flag is raised. And then there's some content in hex, and then there's the equivalent content if it's translatable into ASCII. And you can even see a sequence number, and you can see a length, and then we can see that it is using TCP. So, okay, so we did get a SYN ACK back. It responded back within just a couple of milliseconds, 15.7 milliseconds. All right, so we got something back, a SYN ACK, no loss. Excellent. Okay, so then what if we did not specify any port? Let's take out that TAC-P, and no port at all, which means it should be to port 0 by default. Press enter. And what we got back was a reset ACK saying, are you kidding? I don't listen on port 0. What are you talking about? And you can see here, it's coming in from Kali here, going to Metasploitable port 0 right there. And you can see the SYN flag raised here. And it's sending back a reset ACK saying, sorry, that port's not open for business. All right, let's try some others. Let us try against port 80. So we are going to slip in after a count of 1, TAC-P for 80. Let's go after port 80. And let's see if we get anything. And we can see here that Kali on 50, well, there's an ARP there. Kali on 5150 was going to Metasploitable on port 80 right there. It sent a SYN flag, and we can see that we got back SYN ACK, which is what we expect. And here's, to port 80, we expect the SYN ACK back on a normal TCP handshake. Now, what if we sent this to a port that we're not listening on? We tried that with no port, which means it tried to send to port 0 by default. What if we just pick some other port? Let's just try some other port here, see what happens. So we can see that this thing, scroll back, got to get past some of these ARPs. So Kali was trying to talk to Metasploitable on port 70. Kali was trying to start the handshake with the SYN flag raised, but Metasploitable sent back a reset ACK saying, sorry, I'm not listening on that particular port. And we can try this using a variety of different ports. But what if we wanted to try to test a firewall? Because maybe you have a personal firewall on a machine, and this was particularly true back in the old days of packet filtering firewalls that just had simple rules, and they didn't think of all possibilities. So we wanted to see if we could set some weird flags and see if the host would respond anyway, and see if we could maybe get past the firewall with some weird flags raised. So instead of a SYN flag, what would happen if we were to send an ACK flag? Why don't we try an ACK flag here instead of a SYN flag? Hit enter, see what happens. And it sends back a reset saying, but we didn't have a handshake. What are you talking about? We're just reset. I mean, we never started a handshake. So this is this thing here. Kali going to this target with, and on the flag, we've got, let's see, where is it? We've got an ACK flag raised. And it's sending back saying, well, wait a minute, we never did a handshake. Well, what are you doing? What are you talking about? So now, and it's kind of funny how sometimes the flags show differently here, but we know that with the ACK flag going to it, we got and we know we set the ACK flag, that we got a reset coming back. What if we tried something different? What if we tried to send a SYN ACK? Meaning that we're almost done with a handshake. And let's try that one. What happens when we do that? Well, we get a reset back as we expect. Okay, forget the ARPs here. It's interesting how it ARPs. And what's going on actually is the reason why the target is getting this ARP is because ARP is a broadcast and everybody gets it. So in this case, we have a SYN ACK, or SYN dot as it's showing here. And it's coming back and saying, but reset. Why are you trying to start in the middle of everything? What if we were to raise the reset flag? What if we were to just raise a reset flag? In the old days of the early firewalls, you could sometimes get all sorts of weird responses that the firewall was not supposed to do just by packet crafting like this, by raising weird flags that aren't normal or legal. In this case, we have a reset flag raised. And here's the incoming packet with a reset flag raised. And in this case, we have 100% packet loss because it's like we told the other side that we're done. So the other side didn't respond at all, saying, okay, we're done. No acknowledgement, nothing. We're done. So we have no packet. We have 100% packet loss and no response whatsoever. And what if we did something like really weird, like FIN-ACK? I mean, how do you do a FIN-ACK unless you are right at the end of a goodbye handshake? So let's try that one. So we can see FIN-ACK coming in here. And the other side says, yeah, FIN-ACK, we're done, baby. You're right. Because that's part of the four-way goodbye handshake. You know, with the three-way hello handshake in TCP, it's SYN-ACK, ACK. But in the goodbye handshake, it's FIN-ACK, then ACK back, then FIN-ACK the other way, and ACK. So this is the sort of thing we can do with packet crafting. Now, we could also try something really kind of weird. We're going to set an urgent flag here to TCP urgent. What if we set this as an urgent and a push and a fin, in other words, a Christmas tree scan right here? What would it do if we set it to Christmas scan? Hit that, and we can see that we got back a reset ACK saying, I don't know why you're trying to send me these weird, crazy flags here. Now, there's one more thing we can do. We can actually have hping put into its content something from a file, which is kind of fun. So I have just a really simple file out here. It's a really simple GET request to a web server. Now, it's not going to exactly work because we're not doing a three-way handshake. But just so you know, it's this really simple text right here. I'm going to ask hping3 to populate its packet with the contents of that file. You see the opportunity here for covert channels and hiding data inside of a packet. And the data may or may not be recognized by an IDS, especially if it's like text messages, and IDS probably won't recognize that at all. But we would be sneaking traffic through our network, maybe exfiltrating data that way, just hidden inside of packets. So let me hping3, and let me just send one, taxi count of 1. And the port, I'm just going to use the HTTP port. It's actually going to fail because we're not doing a handshake. 80. I'm going to set the ACK flag. I'm saying that the data size is 20 bytes. You have to actually say the TACD and the size of the data in 20 bytes. If you don't do it, it's going to yell at you and not run. And the file, TAC file, is in root. That's the root user's profile, and the file is called get. And then, of course, the target, 192.168.98.155. Now, watch what happens over here up top when we send this thing. You can see that we actually put into the packet, into the body of the packet, this text right here. And so that is how we were able to sneak something in as just part of the normal packet. And that is how we use hping3 to do packet crafting. In this activity, we will use ZenMap to fingerprint operating systems and services. What ZenMap will do is it will try different TCP flags and different options to see how the operating systems respond, because that kind of signature gives a clue as to what the OS is. I have two VMs ready. One is an XP machine, one is Metasploitable. I don't know the IP address of the XP. It doesn't matter. We're going to ask ZenMap to discover it. Metasploitable, however, I do know its IP. You can open as many VMs as you like. You can just open one if you like. You can even just scan your own machine. If we go to nmap.org, we can see in their reference guide, in the options summary, all of the different nmap switches. When we use ZenMap, it's a GUI front end, and they have some pre-set up scan types here. But we don't know just by looking at this exactly what the nmap switches are until we pick one. If we pick Intense Scan, we can see it's an nmap TAC T4, TAC capital A, TAC small v. If we look over here, we scroll down a little bit here, we can see that a TAC capital A, which is, here it is right here, enable OS detection, version detection, which would mean for the services, script scanning, and traceroute. The T will stand for the timing, the speed. We can do T 0 through 5, 0 being slowest and 5 being the fastest. So T4 would be almost the fastest. With Nmap, usually a T4 is considered reasonably okay. T3 is the average. T5 is sometimes so fast that it might be a little unstable. Since I don't know the IP addresses of all of these, I'm just going to do a quick scan to discover. Let me just do like a ping scan. And let me just discover the IP addresses of these two things here. So let me just put in my subnet ID, 192.168.182.0/24. With Nmap, you can put in /cidermask, or say 1-5, or 1, 3, 27. There are a number of ways to specify hosts. Let's ping the whole subnet to see what we discover. We'll click Scan. And we have 182.129, 131, 132, and 254. Well, I know that .1 is my machine. I'm pretty sure that .129 is Kali Linux. And then we have 131 and 132. According to Metasploitable over here, it's 132, so XP is probably 131. 254 is probably the VMware app itself. So I think I'll focus on 131-132 for scanning. Let's change the target to 192.168.182.131-132. We'll just scan those two. And what kind of scan do we want? We could do a quick scan. Let's do a quick scan. What would that give us? Click that. This would be what we call a fast scan. That -F means the top 100 ports, the 100 most popular ports, at almost the fastest speed. Let's just try that. Nmap is done. We have two addresses, two hosts are up, scanned in almost 7 seconds. The first one here, 131, see its MAC address here. It says VMware, but that's because it's a VMware virtual machine. This is clearly a Microsoft port, unless this thing is a honeypot. So this is a Microsoft machine. No other machine type listens on TCP 135. 139 is the old SMB file and print port, and then the more modern one is 445. So pretty good guess that this is Microsoft. This one down here, 132, we know, because we're whiteboxing it, we know that this is Metasploitable, and we know that's an Ubuntu, and it's listening on a ton of ports, which we have seen already. All right, that's pretty good. Quick scan. What if we wanted to identify the operating systems? What if we looked at this and we said, well, we can guess, but we're not sure. Let's change the scan type. Let's go to Quick Scan Plus. Click that. And we can see that this V means it's going to try to interrogate versions of services. It'll go at almost the fastest speed. The O means try to fingerprint the operating system. And then the F means go for the most popular 100 ports. Let's go for it. Let's scan. Hit it. It's all done. We'll scroll back here. We still see the same ports here. However, it does identify it as either being XP or 2003. And we can see that it is XP SP2 Professional or Windows Server 2003. That's cool. If we scroll down to Metasploitable, 132 right here, we not only see the open ports, but we also see the version. And this is the good stuff, because this is what we do research on to see if there's maybe a Metasploit module for this or some other exploit we can use. So VS FTPD version 2.3.4, OpenSSH 4.7, Linux Telnet D, ISC Bind 942, Apache HTTPD, that's the D stands for daemon, meaning service, version 2.2.8. We have Samba. So this is the Samba server. That's the Microsoft file and print service. They reverse engineered it. There's Pro FTPD on 2121. MySQL 5051A on 3306. Boy, there's a lot of information here for us to research. That's great. And by the way, it identified the host as Metasploitable right there. Did it identify the XP machine? No, I see the operating system, but I don't see the name. That's good. We fingerprinted the operating system and we got a bunch of version information. How about some other kinds of scans? Let's see what else there is here. What if we did an intense scan? What would that be like? Intense scan, no ping. The capital P small n means don't ping. And this means we're trying to get verbose output, and we're fingerprinting the OS as well as getting the service versions, and we've already done that, so we probably don't care about that. We have what we need there. Any others? Ooh, we could do Intense Scan plus UDP, Intense Scan all TCP ports, Slow Comprehensive Scan. It's if you have a lot of time to spare and you're trying to fly under the IDS radar. You have a bunch of choices here. When we get to Nmap, the command line version, we'll study this in greater detail. Until then, let's go on to the next topic. Let's talk about something you're going to need to know in great detail, and that is Nmap. I introduced it in the other topic, but now let's focus on Nmap specifically. Nmap, or the GUI version ZenMap, is open source, super flexible. You can download a version for Linux or Windows. Kali Linux, in fact, most Linuxes already have Nmap built into them. Features. These are just the most popular features. Host discovery, port and service discovery, fingerprinting, OSs and services, enumeration, MAC address detection, vulnerability and exploit detection. The usage is Nmap, and then whatever scan type, any options, and those are optional, and then whatever the target is. You need to keep that in mind. Here are some examples here. You can just say Nmap, whatever the scan options is, whatever the target. You can combine certain switches, like you could say Nmap TAC SU or TAC SV or TAC SUV, and then the target. you can refer to a target by name, IP address, range, whole subnet. So let's start referring to the target. Nmap, single host by IP. Nmap, whole subnet based on the subnet mask. Nmap, whole subnet, well, not whole subnet, but whole range in the last octet. If this was a 24-bit mask, it would be the same. Nmap by name. Now, the name has to be resolvable, so your client is going to do a DNS lookup to try to resolve this name before it scans. Or Nmap, a particular range, like 192.168.0 from .50 to .100 plus 1.50. Notice the comma in there. Here would be an example. We say Nmap some specific target, and this is the results we might get back. Different ports, their status, and the service behind them, and the MAC address of the target. Plus also, it tried scanning 991 other ports, but they were all closed. By default, if you don't specify what ports to scan, Nmap will scan the 1,000 most popular ports. Some people might say the top 1,000, but that doesn't mean from 1 to 1,000. That means the 1,000 most popular ports. So this is Nmap in its most basic usage. If you want to get help on Nmap, you would say Nmap TAC-H. Now, keep in mind, Nmap is case sensitive. So you would type in Nmap space dash small h. That gives you help. Or if you want to see your particular version of Nmap, you would say Nmap TAC capital V. What version of Nmap are you running? If you want to be able to debug, to view all steps, then you would Nmap TAC small d and then whatever the target is. For discovery scans, Nmap can do ARPs, can do ICMP echoes, can do TCP SYNs and ACKs or ICMP timestamps. If you Nmap TAC cap P cap R, you're doing an ARP scan to a target or a range or whatever your target is. This is good because on a LAN, ARPs are not blocked by firewalls, well, usually. The TAC PR, cap P, cap R is actually the default discovery method for Nmap. If you want to specify it has to be ICMP, then you have to do something else. If you say Nmap TAC small s, small n, and the small s means scan, this N means no port scan. I just want to do discovery only. And it will try combinations. It'll try ICMP echo and timestamp and TCP SYN and TCP ACK. Try all of these to do target discovery. If you TAC cap P cap S and then a list, it will send a TCP SYN to the specified ports in the list. The default, if you don't have a list, is port 80. Any reaction from the target, SYN, ACK, reset, tells us that the target is up. Whether the port is open, that's a whole other issue, but the target is up. The syntax shows there's no space between the P and the S, the TAC, cap P, cap S, and the port list. So even though I show port list here, you would start with the ports immediately afterwards. No space. This discovery will be followed by a port scan unless you also specify TAC small s, small n, saying, I just wanted to do discovery. If you don't follow it with this, it will do a port scan of things it discovers. Here's an example of an Nmap ARP scan. So I'm going to Nmap TAC PR, cap P, cap R, some subnet here. And since I did not say TAC small s, small n, it will also port scan after it does the ARP discovery. And so we can see that for the first one, just the first one, only 2 ports were open, 998 were filtered, meaning we got no response whatsoever. And here's the MAC address of this first thing that we scanned. And then, of course, since we're scanning a whole subnet, there might be others after this one. If you want to do basic TCP and UDP port scans, here are the options. Now remember, the small s means scan, and then a capital letter, whatever that is, means the type of scan. So TAC small s cap s means a SYN scan, a stealth scan, a half-open scan. So I'm going to do a SYN scan against one specific host. And it's going to just send a SYN packet to see if it gets a SYN-ACK back. If it gets a SYN-ACK back, port's open. If it gets a reset, it's closed. If it gets nothing, then there's a firewall blocking it. It's filtered. In order to do a SYN scan, a half-open, a stealth, you need to have root privilege. If you don't have root privilege, if you start this scan with this setting right here, with this option, and you're just a Joe Blow user, it will do the next thing. It will do a full scan, a complete scan, a connect scan, the full three-way handshake. It's for the non-root users. If you want to insist upon a full scan, then it's SCAP-T. So make sure you're clear on the difference. If you SCAP-U, we're saying a UDP scan. Now realize that's going to be slow. And ports that respond are open for sure, but realize that not all ports are going to respond to just a probe packet. You might have to actually do something on that port to get any kind of response. We talked about that earlier. Ports that do not respond are displayed as open filtered. Now, filtered always means unknown because we had no response whatsoever. A port might be open, but will not respond to an empty UDP probe packet. If you get an ICMP unreachable, type 3 code 3, then that means the code or the port is for sure closed. Here's an example of an Nmap SYN scan right here. So Nmap TAC small s cap s some target. I'm trying to scan, and I didn't specify the ports, so it went for the 1,000 most popular. 996 of them turned out to be closed, but these are open. And looking at TCP 135, unless this thing is a honeypot, that is a Microsoft machine, because only Microsoft uses 135. Here's an Nmap TCP Connect scan example. So small s cap T to some target here. And again, we tried the 1,000 most popular, 996 are closed, but these 4 were willing to complete a handshake. Here is a UDP scan, and we are doing SU cap V. We want version information if we can get it. So we're doing a UDP scan of one target, and it takes a while. And it comes back with, oh, we found 999 ports that are either open or filtered. We had no response whatsoever, so they're one or the other. However, we know for a fact that port 137 UDP is open because we did get a response. So we know that much. And based on what we got back, we think this thing is Windows. All right. You can also do list scans and service version scans. So if you do an Nmap TAC small s cap L, that means we want a list of what we're going to scan. Remember how I talked about a list scan? We're just going to do a DNS lookup. If I give an address, it's going to give back a name by doing a reverse DNS. If I give a name, it's going to give back an address. So I'm going to just list and then whatever I give, like 422 star. Okay, so give me back all of the addresses that we could scan with the names that are 422 something. That would be the Verizon DNS servers. Or give me back all of the IPs for eccouncil.org. So this is a way of doing passive recon because we're not really scanning those targets. We're just getting more info. We could smallest TAC or TAC smallest cap V for service version. So we want version information against a particular IP address. This might help us get more information about UDP scans to help what we call disambiguate them, get more details. Here's an example of a list scan. Okay, so let's list 4221-6, and we can see that there's actually a name for 4221-23456. These are Verizon DNS servers. You know how like Google has DNS servers, 8.8.8.8, 8844? Well, these are the Verizon DNS servers, and they have been around since before Google. And these are actually their names right here. So they're up. We didn't truly scan them, but we did research on them. Here's the service version scan. So attack small s gap v against some host, and it's scanning these. It found that only 4 of the ports of the 1,000 most popular are open, but it tried to give us the version of whatever the service was behind it. In this case, we did find out that the HTTP API is version 2.0. Here are some Nmap options. You want to specify particular ports? Then you say tac small p and then the range or the specific port. And it's going to be TCP unless you are specific. So let's say we only want to scan TCP 80, then we'll say nmap tac p 80 against the target. Or nmap tac p 80, 443 against a target. Or a range from 1024 to 3000 against a whole subnet. Or if you want to specify UDP, you say tac small p cap u colon the port number or port numbers. So in this case, we're scanning for UDP 53, 111, 137. And then if you say T colon, then we're scanning for TCP. You see, you don't have to specify T, you don't have to say TCP unless you are intermixing it with UDP. You have to say U for UDP, but you don't have to with TCP. So like up here, this first one, tac p 80, it's assumed it's TCP. 8443, assumed it's TCP. 1024 3000, assumed that it's TCP. But this next one, UDP 53, UDP 111, UDP 137, then TCP 21 to 25, and 80, and 139, 443 against this subnet. See that? Or, if you want to scan all ports, all TCP ports, 65,535 of them, because we don't scan 0, you would say nmap tac p tac. Now, that's going to take a while. Nmap will scan things randomly, okay? Because if you go port 1, 2, 3 like that, you're going to set off an IDS fast. If you want it to be consecutive and not random, and it's not going to gain you any performance, but if you do want it to be consecutive, you would say tac small r. If you want to scan just the top 100, 200 ports, and when I say top again, I mean most popular. I don't mean like from 1 to 100. I mean the 100 or 200 or 300 or 50 most popular ports. You would say nmap tac top tac ports, the 200 most popular, or the 50 most popular. If you want to scan IPv6, you would say nmap tac 6, and then in this case, that's IPv6 address, or a resolvable name. Or this too is an IPv6 address, but it is a linked local address, not a public address. So that's how you would scan IPv6. I hope you're taking notes because you will need to know this stuff. You will need to be able to type this stuff in the exam. If we want to scan hosts listed in a file, now do not mistake this for a list scan. List scan is where I just either resolve IPs to names or names to IPs, but I don't scan anything. Scanning hosts listed in a file, capital L, means I'm going to have a text file of some kind, and I'll just list all the hosts, and you read the file and scan those. So make sure you're clear on that difference. If you want to scan some subnet or some range or group, but exclude something, you could say tac exclude. So like in this case, nmap, and it's supposed to be an N, nmap, whole subnet, tac exclude 192.168.1.5. If you don't want to resolve names, which will save time, tac small n. If you want to try to resolve all names, tac cap r. If you want to do fast mode, and this is a time saver, fast mode will scan, I think, the top 100. So that's why it's faster, because it scans fewer. Not that it's going any faster in terms of speed. So tac cap f speeds things up just because you're doing fewer ports. And I'm pretty sure it's the top 100. Tac capital O, not 0, this is an O, will try to detect the OS, but it's not always accurate because many operating systems have similar fingerprints in terms of their TCP/IP stack. TAC-CAP-A is pretty comprehensive. It will try to do OS detection, service version detection. It will scan with popular scripts and do a traceroute to the target. If you want to specify how hard you interrogate a service to figure out what it is, you can say the version intensity. So remember how TAC small s cap v is try to figure out the version? We could then say TAC version TAC intensity from 0, which is very lightweight, to 9, which is attempt all probes. Obviously 9 would take longer. We're trying much harder to figure out what this version is. You can also specify a script. There are many Nmap scripts. Nmap has a scripting engine, NSE. So you would say nmap tac script equals, and then the name of the script, and then the target you're going after. Please don't think that this is separate lines. All of my examples here are typed on one line. If you want to scan using the default scripts, just throw all the default scripts at it, tac s cap c. If you want to get verbose output, more details, tac small v. If you want very verbose output, tac vv. You want to specify what the output looks like. What is the format of the output? Then it's tac small o, n for normal, x for XML, s for something that script kiddies can read, g for something that's searchable, greppable, a means give me one in every format. So we've already seen this, the stealth scan, small s cap s. That's the half-open stealth scan, SYN scan. Do not complete the handshake. You send a SYNAC, or you send a SYN, they send a SYNAC, you reset. This is less likely to be logged by the target because it's not a true connection, however, more likely to be noticed by an intrusion detection system if you do too many of these all at the same time. If you just want to assume that hosts are online, just start port scanning. Whether they're up or not, you don't know. Skip the discovery. Just tac cap p small n. You do this if you know that the firewalls are going to make it hard to discover. They are not on your subnet, so you can't do ARP effectively. They're on some other subnet. Just start port scanning. You know they're not going to respond to ICMP. Just start port scanning. Obviously, if you scan like a whole subnet, be prepared to order a pizza and sit down and watch a TV show or two before you're done. So just so you know, it will take a while. If you want to do an ACK scan, tac small s cap a. Remember, small s means scan, and then followed by capital something for the scan type. So we can use the ACK scan, as we've seen before, to find out if a host or a network is protected by a firewall. If the result says filtered, means we've got no response at all, so a firewall is on. Unfiltered results could indicate the port is accessible, might be open or closed. We would run the TAC A option to determine if accessible ports are actually open or closed. So look at this. We would say ACK scan and then TAC A after that, don't combine these, to determine a little bit more. Is the port open or closed? And here's an ACK scan example. So I did an ACK scan to this one thing, and 999 of 1,000 ports gave me no response at all. They were filtered. But one of them was unfiltered, SSH22. Then, of course, if you want to do the Christmas scans or the fin or the null, here they are. F for fin scan, only raise the fin scan. We can use it to help sort of figure out or disambiguate results from other scans. The null scan, cap n, no flags. Sometimes it can penetrate a firewall or an edged router. An open port will discard it with no response. A closed port will send a reset. And then, of course, X for the Christmas scan. We raised fin, urge, and push all at the same time. So these scans can be used to sneak through some stateless firewalls. It works against mostly Unix-based systems, not Microsoft, and only some Cisco. You want to do zombie and bounce scans? Why not? So the zombie scan is also known as the idle scan. So small s cap I for idle, and then the whoever zombie is. So the first thing is find me a zombie. So you'll nmap tech small s cap I something. Let me see if you're a zombie or not. And if it is a zombie, if it comes back and says this is a zombie, then you idle scan zombie IP, your true target IP. So in this example here, I'm going to do an idle scan, a zombie scan, without bothering to ping. We assume the target is up. Give me a scan of every single port in the TCP universe, bouncing off of this zombie to this actual target, www.company.com. The zombie is the middleman. If you want to do a bounce scan, an FTP bounce scan, you have to find a suitable FTP relay. So you would say nmap tac B, who you're going to bounce off of, and then the target. Now remember, the target doesn't have to be an FTP server. It could be just anything that can be port scanned. One cool thing about nmap is its ability to decoy and spoof. So, you're going to need to know this. One way to evade IDS is to split the packets, including pings, into 8-byte fragments. Fragment the packets. They're so small that their signatures aren't complete, so intrusion detection will not recognize them as malicious packets. So you could nmap tac F, and the default is to split a packet into an 8-byte fragment. So nmap tac F, small f, your target. If you want to create a bunch of bogus noise by hiding amongst a bunch of fake decoys, I know, isn't that funny? Fake decoy. but that's the case, you know. You could say tac capital D, and then you could indicate phony IP addresses. They don't exist. You're making it look like they exist. So I want to decoy, and I have 3 bogus targets. Those decoys will look like they too are scanning. The real target is 1.50. It then becomes really hard for IDS or the administrator to go, well, which one is doing the actual scanning? 4 of those, this original one plus these 3 decoys are all seemingly scanning 1.50. So that's how to hide amidst a bunch of spoof decoys. If you want to specify scanning out a particular interface, you can say tac small e and then the interface, like Ethernet 0, and then whatever you're scanning. If you want to spoof your source address, you could say out Ethernet 0, I'm spoofing my source address. Because you're spoofing, you're not going to actually get responses, but it will confuse an IDS or a target administrator. And what's good about it is there may be cases where you don't, if you get an actual response or not. Or maybe you're doing things where all you care about is just creating noise, or you'll just see what the broadcast is, or you'll just, you'll sniff the traffic or something like that. So you can spoof the source address as well. You can spoof the MAC address. You could create a bogus MAC address, specify either something random, or you can explicitly say, I want the MAC to look like this, which hides the actual source of a scan. Now, obviously, you won't directly get a response back, but if you're doing this with, say, an ARP ping scan, doesn't matter, because ARP does broadcast anyway, and there's no specific target. You could also specify the source port number. Now, this is really good because you might have firewalls that say, like, okay, I'm not allowing just any old source port coming in, but I will allow source port 80 because that's obviously one web server talking to my server, or I will allow TCP 53. That's one DNS server replicating with my DNS server. So if you want to spoof your source port, you can do that. And it creates these packets that have a fake source port, which could dupe a packet filter if that packet filter is configured to trust a particular source port. You could also randomize the order in which the hosts are being scanned. Instead of going 1, 2, 3, 4, 5, you could go like 1, 17, 53, 2, 85. It would bounce around. That too might help throw off an IDS that would be looking for incrementing patterns like that. 1, 2, 3, oh, that's obvious. You could also Nmap through proxies. You could go through a chain of anonymizers on the internet, either HTTP or SOCKS proxies. And SOCKS is a Unix Linux connectivity protocol. This is really good when you're doing scanning on the internet. You don't want people to be able to trace back to you. You can also specify timing for Nmap. So you can say TAC capital T after you specify whatever other options from 0 to 5. So I can say Nmap this subnet TAC capital T2. It will use different timing templates to throttle the speed of your queries. The slower, the less noticeable to scan. So T0 is the slowest. T5 is the fastest. Nmap denotes these speeds as paranoid, 0, sneaky, 1, polite, 2, normal, which is the default, T3, aggressive is T4, and insane, T5. Now, T4, if you want to do a fast scan, T4 is recommended because T5 might be a little unstable. If you don't specify the timing, then T3 is the default. Now, you really need to have a handle on Nmap, its syntax, and how to use it. Make sure you practice this a lot. And that's our look at Nmap. And now, let's go on to the next topic. Let's perform some basic Nmap commands. In the exam, you will be expected to know Nmap really well, so we're going to spend a lot of time practicing on it. You can open up your CEH v12 mod 3 snippets, and you can either just copy and paste these commands, but you'll have to edit them first, or you can use them as an example and type your own. First, let's scan a single target. The command is nmap and then the target, either by IP or by name. The name has to be resolvable. It has to be in your host's file, it has to be in DNS, it has to be something that can be looked up via MDNS or whatever. I'm going to scan a single target on my network. You will need to change this IP address to suit your environment. I suggest you either pick the address for Server 2016 or Metasploitable. Those will be the most interesting. I'm going to just copy this, and I'm just going to paste it right here. You can usually paste clipboard or selection. In this case, it doesn't really matter. I'm just going to paste that. It's highlighted. That's what Z-Shell does. Here's the keyword. Here's the string. Doesn't matter. The prompt, you may not be able to see it, is already after this command. This highlighting is just for your reference. If you don't like seeing it, find the right arrow key on your keyboard and press the right arrow key. Or you can just leave it. We'll press enter. And that was quick. Let's scroll back. We have the report for that particular target. 977 TCP ports report as closed. The connection was refused. You know, when you scan a port, you can have 3 responses. One is open, like this, meaning I send a SYN, you send me back a SYNAC. I know that that port has a service that's using it. It's open for business. Or I send a SYN and you send back a reset RST, meaning the operating system is telling me there's no service listening on this port. Or in some cases, you can have what's called filtered, meaning you get no response at all. That means there's a firewall preventing any kind of response. For this particular target, I can see that it is listening on FTP, SSH, Telnet, SMTP. When you see 53 TCP domain, that means it's a DNS server. It's a web server. Here is a Linux Unix specific port, 111 RPC bind. It is sort of the equivalent of the Microsoft 135. And then I see two Microsoft ports here, which I don't think this is a Microsoft machine, because Microsoft machines would not use this unless it's a honeypot and it's lying to you. More likely, this is some kind of Linux machine or Nix machine that is running the Microsoft file and print service. Because also this here, 5, 12, 13, 14, these are Linuxy, Unixy based services. And there's some others. Oh yeah, here's NFS. That is the network file system. That's the file sharing protocol for Linux and Unix. I see another version of FTP listening on 2121. I see two versions of SQL, MySQL and PostgreSQL. And I see VNC and X11, which is for generating the desktop. Okay. A couple more things. Oh, IRC, Internet Relay Chat. Who uses that anymore? And then there's one here, 8180, that Nmap could not identify. And then I got to look up whatever AJP13 is. I have no idea. Okay, that is scanning a host. And I see all these open ports, which means possibly these are targets. Because maybe if I'm lucky, some of the services that are listening on these ports have vulnerabilities. So this is the first step to identifying potential services to attack. Let's scan something by name. I'm going to scan on the internet here. Let me just type clear to clear this out. And let me just paste this. Nmap.org makes this server available, scanme.nmap.org. You're encouraged to scan it, just don't abuse it. Let's go, enter. So it's scanning out on the internet. And we do have a few things open. Remember how I said one of the results you could get from an Nmap scan is filtered, meaning no response? In other words, a firewall is disallowing any kind of response, be it open or closed. So of the 1,000 most popular ports, 998 of them for this online target, they're not responding, neither yes or no, which means that there's a firewall filtering those. The firewall, however, is allowing two things to go through. Whether or not they really do anything, we don't know. But this target is able to accept connections, at least it seems like it, on two ports. This is really cute. Elite. That's 31337. Get it? 3 is E, L, E, E, then 7 is T. That's an old one. Let's take a look at some of the other scans. We're going to scan two hosts, number 129 and 131. Again, change this to suit you. I'm going to scan both of these. They're not one after another. They're not in order. They're not contiguous. That doesn't matter. Let's copy this. Come over here. Let me clear. And let me right click and paste. And let's try scanning the two of these. Hit it. Okay. 129 has 992 ports closed. We actually got a response. It was reset for all of those. But it is listening on these. Okay. All right. Port 25, 80, 110, 135, 139, 143. This could be a Microsoft machine, especially with the 135 there. And then it kind of looks like it's also running some email services. Okay. And then 131 here has a few services open. Looks like a Microsoft machine because these are all Microsoft ports, especially 135. Linux machines don't use 135, unless, of course, they're a honeypot. All right, so we have results for 2 machines. Now we'll scan a range, in my case from 128 to 132. I have no idea from my previous scans if 128 or 132 are live, because I haven't tried scanning them, but we'll find out. So let's scan this range. Enter. Give it a moment. Okay, scrolling back, scroll back. Okay, from 128 to 132. 128. All 1,000 scan ports are in ignored states. Connection refused. But the host, 128, is live. It just has no open ports. Okay, 129 we've already scanned before, and we get the same results. 130, here's 130, and that has all of these open ports. Right here, all these nice open ports, possible targets. 131, we've seen this one already, and there's nothing for 132, which tells me that 132 is not responding. Doesn't mean that it doesn't exist, it's just not responding in any way, shape, or form on the network. Finally, we can scan an entire subnet. Now, the subnet, of course, and any of these addresses, they don't have to be on the same subnet as the scanning machine. I mean, they could be across the world so long as I have routing to them. But in our case, of course, we're just scanning our own virtual machines. Let's scan the whole subnet. With this /24 CIDR mask, I am scanning from 0 to 255. Here we go. That was pretty quick. Let's scroll back. We did get a response from 252.2, and it has one open port, TCP53, meaning it's a DNS server. Okay. 128, none of the ports show open, but the host is up. We've already done 129. We've already done 130 with all these open ports. We've already done 131, and that was it, those 5. Everything else did not respond. So that's really basic Nmap scanning. Let's do a little version detection using Nmap. I have 2 VMs here. I have Metasploitable, and I have Kali Linux. I've logged into Kali just as the Kali user. In Metasploitable, I'm just going to log in to double check the IP address. Let me just do that. So I'm logging in as msfadmin, press enter, same password, msfadmin, enter, and then I'm just going to type ifconfig, enter. My Metasploitable is 192.168.252.130. Yours will obviously be different. Let me come over to Kali, click over this, and ifconfig on Kali. And let me scroll up a little bit here. Kali's address is 192.168.252.128. Let's just make sure that Kali can ping Metasploitable. Ping 192.168.252.130. And yes, it's successful. Press Ctrl-C to break. All right, this is good. Nmap has 3 switches that we can use to do version detection. Kind of depends on how far we want to go with it. If we just type nmap tac H for help, press enter, we can see some of this already. Let me just scroll up a bit and kind of start from the top. I see some of it as we go by. Okay, so coming down here, there are three I would like to point out to you. One is Nmap TAC small s cap v. That will probe the service version. So that's one. Another one is Nmap TAC capital O. That will do OS detection. Doesn't always quite work. You can try to guess a little more aggressively using this script if you want. And then there should be another one that is listed down here, and if I don't see it right off the bat, I'll just tell you what it is. Okay, there's TAC capital A. It will try OS detection, service version detection, script scanning, and traceroute. We're just going to try all three of them. We already know how to do a basic Nmap scan, so let's just try Nmap TAC capital O, not 0, capital O, and then our target, 192.168.252.130. Let's see if it can guess the operating system version. Press enter. Oh, and it's saying I need to do this as root. Whoopsie. Okay, sudo nmap TAC capital O 192.168.252.130. Press enter. And the sudo password for Kali is Kali. Press enter. Okay. Give it a moment. All right. OS detection performed. Okay. And it says that this is Linux 2.6 something with the Linux kernel 2.6. So that's as much as it can say. It's either 269 up to 2633. So that's its best guess. All right. Fair enough. And it shows various ports that are open. Great. Well, how about if we try to do the S cap V? Because when I look at the open ports, it doesn't give me any version information. It tells me what they are, but it doesn't say like version 2.3 or something like that. So let's try nmap. Let's see if we have to sudo nmap TAC small s cap V target 192.168.252.130. Hit it. And it doesn't prompt us for the password because we just provided it just recently. Let it run for a little bit. Pause the video. Oh, there it is right there. Okay. So here it has interrogated the services. So the FTP is VS FTPD 2.3.4. And the SSH is OpenSSH 4.7. Oh, and look at this, Debian Ubuntu. You know what? That is kind of a hint that, although we know the Linux kernel, that this is an Ubuntu box. And actually, Metasploitable is Ubuntu. And then let's see, we have the postfix SMTPD, and we have the DNS bind 942, and Apache HTTP server 228, and Samba SMBD 3.x to 4.x. So this is good. We have some, yeah, there's even more here. Look at this, Pro FTPD on 2121, PostgreSQL 8.3.0 to 8.3.7, all good. All right, so we've tried two of those. Now let's try the comprehensive one. Nmap, let's sudo it just in case we need to. Sudo nmap TAC A, all of it, or something. I'm not sure if A stands for all, but whatever. 192.168.252.130, go for it. All right, as we scroll back, we can see the SMB NetBIOS name, Metasploitable. That's cool. We can go back even farther here. We can see a clock skew. That's nice. So here's some SMB information, and this is Samba 3.0.20 Debian, which again backs up the thought that we are a Debian machine. Okay, great. And as we continue going backwards, there's more, the same information about the Linux kernel, and it says what the various script results are here. going back, and it tells us just greater detail about all of this stuff. This is so good. So these are the 3 ways that you can do version detection using Nmap. And then you take that information and you do a little research. What are the vulnerabilities and exploits of some of these versions? And with that, let's move on. Let's do a little version detection using Nmap. I have 2 VMs here. I have Metasploitable and I have Kali Linux. I've logged into Kali just as the Kali user. In Metasploitable, I'm just going to log in to double check the IP address. Let me just do that. So I'm logging in as msfadmin, press enter, same password, msfadmin, enter, and then I'm just going to type ifconfig, enter. My Metasploitable is 192.168.252.130. Yours will obviously be different. Let me come over to Kali, click over this, and ifconfig on Kali. And let me scroll up a little bit here. Kali's address is 192.168.252.128. Let's just make sure that Kali can ping Metasploitable. Ping 192.168.252.130. And yes, it's successful. Press Ctrl-C to break. All right, this is good. Nmap has 3 switches that we can use to do version detection. Kind of depends on how far we want to go with it. If we just type nmap tac h for help, press enter, we can see some of this already. Let me just scroll up a bit and kind of start from the top. I see some of it as we go by. Okay, so coming down here, there are 3 I would like to point out to you. One is nmap tac small s cap v. That will probe the service version. So that's one. Another one is nmap tac capital O. That will do OS detection. Doesn't always quite work. You can try to guess a little more aggressively using this script if you want. And then there should be another one that is listed down here, and if I don't see it right off the bat, I'll just tell you what it is. Okay, there's TAC capital A. It will try OS detection, service version detection, script scanning, and traceroute. We're just going to try all 3 of them. We already know how to do a basic Nmap scan, so let's just try Nmap TAC capital O, not 0, capital O, and then our target, 192.168.252.130. Let's see if it can guess the operating system version. Press enter. Oh, and it's saying I need to do this as root. Whoopsie. Okay, sudo nmap tac capital O 192.168.252.130. Press enter. And the sudo password for Kali is Kali. Press enter. Okay. Give it a moment. All right. OS detection performed. Okay, and it says that this is Linux 2.6 something with the Linux kernel 2.6. So that's as much as it can say. It's either 269 up to 2633. So that's its best guess. All right, fair enough. And it shows various ports that are open. Great. Well, how about if we try to do the S cap V? Because when I look at the open ports, it doesn't give me any version information. It tells me what they are, but it doesn't say like version 2.3 or something like that. So let's try nmap. Let's see if we have to sudo nmap tac small s cap v target 192.168.252.130. Hit it. And it doesn't prompt us for the password. because we just provided it just recently. Let it run for a little bit. Pause the video. Oh, there it is right there. Okay. So here it has interrogated the services. So the FTP is VS FTPD 2.3.4. And the SSH is OpenSSH 4.7. Oh, and look at this, Debian Ubuntu. You know what? That is kind of a hint that although we know the Linux kernel, that this is an Ubuntu box. And actually, Metasploitable is Ubuntu. And then let's see, we have the postfix SMTPD, and we have the DNS bind 942, and Apache HTTP server 228, and Samba SMBD 3.x to 4.x. So this is good. We have some, yeah, there's even more here. Look at this, Pro FTPD on 2121, PostgreSQL 8.3.0 to 8.3.7, all good. All right, so we've tried two of those. Now let's try the comprehensive one. Nmap, let's sudo it just in case we need to. Sudo nmap tac a, all of it, or something. I'm not sure if A stands for all, but whatever. 192.168.252.130, go for it. All right, as we scroll back, we can see the SMB NetBIOS name, Metasploitable. That's cool. We can go back even farther here. We can see a clock skew. That's nice. So here's some SMB information, and this is Samba 3.0.20 Debian, which again backs up the thought that we are a Debian machine. Okay, great. And as we continue going backwards, there's more, the same information about the Linux kernel, and it says what the various script results are here going back, and it tells us just greater detail about all of this stuff. This is so good. So these are the three ways that you can do version detection using Nmap. And then you take that information and you do a little research. What are the vulnerabilities and exploits of some of these versions? And with that, let's move on. Let's try an FTP bounce scan using Nmap. Once upon a time, FTP servers had a feature that was enabled by default called the File Exchange Protocol, FXP. The problem with that was that it became very easy to, instead of just asking an FTP server to do some file exchange, it became easy to ask the FTP server through its command port 21 to perform some other kind of command, such as a port scan of some other machine. I have several machines open here, several VMs. I have Kali, and I have Metasploitable, bbox, and Server 2016. Metasploitable has been configured in setup to be vulnerable, to allow FXP, because these days it is disabled by default on FTP servers because the bounce scan attack was so prevalent. I also have bbox, which has not been modified. It has an FTP server that is somewhat vulnerable, but we'll see what happens when we try to use it as an FTP bounce proxy. In other words, the machine in the middle that we're taking advantage of. And then Server 2016 is the ultimate target. So these three machines could be hiding behind a firewall, and then the firewall allows a port to go in and talk to either Metasploitable or bbox. And then Server 2016 is not accessible from outside the firewall at all. This is just sort of a made-up scenario. So what we're going to try to do is we're going to try, first of all, doing the bounce scan, trying to bounce through bbox, which is in my case, 192.168.252.134, and then server 2016 is .129, so that's the ultimate victim. So what I'm going to try to do here is I'm going to nmap tac verbose, tac bounce, and then some name, anonymous, colon, so it's name, colon, password, let me in. And quite frankly, the password, when you have anonymous logins, the password is completely unimportant. Okay, and then at the IP address. Now, here's where we're going to try first bouncing the attack through the B box. So at this address, .134, at 192.168.252.134, and then the actual target, which is server 2016.129, 192.168.252.129, then we'll tell it to not ping, just go for it. And go for the scan directly on ports. We're just going to see if the target, which we cannot reach directly, is listening on TCP 21, 22, 23, 25, 80, 110, POP3, 443, which is HTTPS, and 445, which is the new SMB file and print port, but, well, not that new, it's been around for quite some time, but it's the current file and print port, and also for the Microsoft Windows localhost logon service. So that is our command here, rather lengthy. Let's go for it. Let's see what bbox will do with this bounce command. Hit it. Okay, so it says the resolved FTP bounce attack to bbox. Okay, initiating parallel DNS resolution of a host, completed it, attempting a connection. And so it connected all right to bbox's server right here, a Pro FTPD 1.3.1. And the login credentials were accepted, meaning it's accepting anonymous connections. Tried the bounce scan, but your FTP bounce server doesn't allow the privileged ports, skipping them. The privileged ports are the lower end ports. And you didn't want to scan any unprivileged ports. Well, okay. Maybe we can try scanning something unusual. How about, instead of these, I wonder if 3389 is considered privileged or not. 3389, that is for, RDP. Let's try that. And it may or may not accept that. We'll see. Oh, keep going, keep going, keep going. Come on, give us some good news. Come on, come on, come on. No, your FTP bounce server sucks. It won't let us feed bogus ports. Okay, so the bbox FTP server was somewhat vulnerable, but wasn't useful. Let's try using Metasploitable as the bounce proxy. So we're going to do this using 130. All right, up arrow. In fact, I'm going to get rid of some of this stuff here. I'm just going to clear. And I don't want any of this jazz here. Let's just clear the screen. Okay, now up here, let's up arrow, and we're going to bounce through 130. And we're going to attack 129. Bounce through Metasploitable, attack server 2016. And let's try all those ports again. Let's see, what did we say? 21, 22, 23, 25, 80. And you could try whatever ports you like. 110, the POP3. And, why not 143, IMAP? And 443, HTTPS, and 445. And, while we're at it, RDP 3389. Oh, and you know what? And, we don't have to do these in order. I'm interested if this is listening on remote procedure call 135. And how about the old 139 for the old file and print protocol? Okay, I need to change this, not bbox, but Metasploitable. So let me click in here. We're going to bounce through Metasploitable and attack server 2016. So here's Metasploitable's address, and here's server 2016's address. Is that right? Yep, that's it. And don't ping, just go for it, and try to scan these ports. Okay, here we go. Let's try it. Okay, we resolved the FTP bounce attack proxy. So yeah, we were able to identify that is it. Okay, so problem with bounce server, resource temporarily unavailable. That's okay. Our FTP proxy server hung up on us. We're retrying. On second try, look what it found. Oh yeah, it found, oh my goodness, it found all of these. Well, pretty much all of them, huh? It found 21, 22, 23, 25, 80, 110, 135, 139. IMAP 440. Wow, haha. So that is an FTP bounce scan. You're not likely to see any FTP servers these days that have been misconfigured to be susceptible to this. But you never know. And with that, let's try something else in the next activity. Let's take a look at Nmap scripts. I have Kali Linux open. I've logged in as Kali. And I have Metasploitable open. I haven't logged in yet. I'm going to do that. msfadmin, password msfadmin. And all I want from Metasploitable is the IP address. ifconfig, enter. Okay, my Metasploitable IP for me is still 192.168.252.130. You know, sometimes as you reboot machines, they change their IPs. Okay, that's fine. Let me just make sure that I can ping Metasploitable from Kali. Ping 192.168.252.130. Enter. Yes, I'm getting replies. Control C. All right, let me clear this. When you're looking at Nmap scripts, one thing you could just do is type Nmap and then -H for help. You can press enter. And as we scroll back up, you can see some script information right here. So you would either just type nmap --script equals and then whatever the name is, or you could type -s small s capital C to run the default set of scripts, or there are other things we can do as well. Open a browser to nmap.org, and we can search for scripts just by doing a site search, scripts, and press enter. And there's various things to help us, but we're interested in the reference portal, or you can look at usage and examples, but we want right now the reference portal. So let's go to the reference portal, click that. And there are different ways of looking at all the scripts. There are over 600 of these. I think it's like 670 or something like that. It's just an amazing number. This is all of the scripts in alphabetical order. I mean, my goodness, they've got ones on Bitcoin and BitTorrent Discovery, and these are just the B's. Wow, let's try to scroll down quite a bit. There's some DHCP, that's just the D's. I mean, now we have some other ones, Firewalk, Firewall Bypass. Keep going. I mean, the list is pretty extensive, 600 plus scripts, right? So you just might think, well, how am I ever going to find what I want? There are a couple of ways of doing it. Let's scroll back to the top. You could go to categories. Click categories. The scripts, although they show here in alphabetical order, are actually organized in categories. Some of them have many scripts. So like, for example, if I type or click vuln for vulnerabilities, we click that one, this shows me all scripts that have something to do with discovering if the target has a particular vulnerability. And I'm scrolling down, and there's all kinds of, oh, look, check for shell shock. Check for SQL injection, for stored cross-site scripting. Wow, look at that. Some of these are listed by their CVEs. I know some of these are listed by their Microsoft number. Some are just by the name. There's a bunch for SMB. I mean, there are a lot here, okay? So even this, you might just say, oh, it's kind of hard to look at. So another thing you could do, let's just go over to Kali Linux here. you could just look in the file system of Kali to see the scripts there. I'm just going to clear. Now, in Kali Linux, most of the time you will find Nmap scripts in a particular location. We're going to cd into usr/share/nmap/scripts. Okay, we're going to go right there. I'm going to press enter, and we will type ls and press enter. And here's another way of looking at all the scripts. Now, this is still quite a bit, but if you look at it this way, at least you can kind of see them a little better laid out. Maybe, maybe not. You know, it kind of depends. Loads of HTTP scripts, DNS scripts, etc. Maybe I'm still not sure what script I want to run. Some check for vulnerabilities, some try to exploit, some try to log on, some gather information, and I'm still overwhelmed. So I'm just going to run the default script, or actually the default set of scripts. Let me just clear, and let me nmap --script, and then default, or you could also, instead of doing it this way, you could nmap -s capital C, that's the shortcut way of doing it, and then the target. The target is 192.168.252.130. Let's just see if the default scripts turn up anything. Press enter. It will take a moment. I'm going to pause the video and we'll check when it's done. We're done. Let me scroll back and see what we found. Back. It did try a bunch of them. Okay, so it was scanning for ports, and it did find information about just our FTP service right off the bat. It was able to log on as that user and got us some statistical information. Okay. Then it went to this and tried this and said anonymous FTP logon is allowed, and FTP bounce is working, so it's giving us some vulnerability information. It grabbed the SSH host keys, both 1024 and 2048-bit. It went down a little bit farther here and told us about SMTP, including the ciphers that were used, and the cert name and information. Then it went over here to the DNS server, gave us some information about that, and some information about RPC endpoints, and going on a little bit more. It identified various ports and what they were doing, tried to do something against MySQL, gave us a little bit of information, including the salt for the authentication. Oh, that's interesting. All right, was able to grab the banner, I think, from PostgreSQL. So we did get some information here, some information about IRC, and let's see, something else. Clock skew, found out some stuff about SMB. So that's pretty good. That was the default scripts. Now, what if I was interested in trying one of those categories? Let's go back to our reference page here. I'm going to look at the categories again and click categories. Now, I know some of these have a whole lot. Let me see what Fuzzer has. Click that. Oh, Fuzzer only has 3 scripts. We could try that. We could just say --script, and then we could say equals Fuzzer, or just --script space Fuzzer for the category. Let's just try that. And I have to warn you, you run too many scripts against some of your targets, you might freeze up some of their services. So if you're going on forever and it's not responding, maybe reboot the target again. Okay, let's try this. Let's nmap --script and Fuzzer against the target, 192.168.252.130. Let's just see if that gives us anything. There are only 3 scripts. They might all turn up negative, but let's just find out. Again, I'm just going to pause the video until, oh, it happened already. Okay, and let me go back. As is typical of Nmap, it does a typical default Nmap port scan. And right here, it tried a DNS fuzz. It tried that one DNS fuzz script, but it said, didn't respond to our probe, so we can't fuzz it. Okay, so that's the response. So that was the one script that it tried. All right. Let's go and take a look at other categories. You see, so it tried this fuzz right there and it didn't work. What about other categories? If we do DOS, denial of service, we're probably likely to jam this thing up. How about malware? This is searching for malware. Let's click that. What are the scripts that would run? Some of these will have nothing to do with our target, but it's still worth trying. I like this. SMTP strange port. See if SMTP is running on a non-standard port. Okay. How about the Unreal IRCD? See if the IRC server is backdoored. Well, you know what? Let's try the malware scripts. Try the malware categories. So I'm going to come back over here and I'm going to nmap tac script malware to the target 192.168.252.130. Hit it. And we're back already. Scroll back. So we got a little bit of information here. The FTP, VS FTPD backdoor, it says it is vulnerable. It is exploitable. Ooh-wee. You know, there is a script actually to exploit this. And that even gives us some references. That's nice. And let's see, some of these other ports, no, but it does say, the Unreal IRCD backdoor looks like there is a Trojanized version running. Okay. So this is using scripts. Now, again, we could just try a single script. Let me just go to categories here, and let's try vuln. Now, there are a lot of vulnerability testers here. Let's see, is it vulnerable? Well, it did already try this VS FTPD backdoor. Is there another one we could try? I wonder. HTTP enumerates directories used by popular web apps and servers. You know what? Why don't we try that? Script equals HTTP tac enum. Let's just try that. Now, of course, it's going to enumerate based on just a word list, and we might get nothing. But hey, it's worth trying. So let's nmap tac script, and I think you can just, without the equal sign, you can just put in the name just like you would a category. HTTP tac enum. If it doesn't work, we could then say script equals with no spaces, but we're just going to try it without the equal sign. See if we can get away with it. 192.168.252.130. Let's see. Go. We did not get a syntax error. Oh, okay. Hey, look at this. So it used a well-known word list and said, we found admin. We found admin login. Awesome. We found all of these admin pages in the admin ver. Wow. So these were discovered. Nice. And then it found mostly admin and a few manager and one web dev, and it has commentary on them. That's very cool. So this is how we can use nmap scripts. So have some fun with it. Again, if the target just takes forever to respond, you might consider restarting the target because maybe you already jammed it up. Now let's move on. We've talked about nmap and packet crafting. Now let's take another look at that in terms of evading firewalls and intrusion detection. Let's talk about firewalls and scanning. Every firewall is going to have its own little rules and configurations. They will each bring their own challenges to scanning. Now, the default for any particular firewall is connections that are started from the inside going out are allowed. Connections that are started from the outside coming in are blocked. Then we have to make exceptions to these rules. If you're scanning a network black box style where you don't know anything about the internal workings of it, you'll have no idea what type of firewall you'll encounter, if there even is a firewall. Now you can infer which type of firewall you have by how it responds, by what it does. That'll give you an advantage in a pen test. You'll have a better idea of which techniques you don't want to waste too much time on and other approaches you should try to break into the network. Nmap will report back on ports in one of three states: open, closed, or filtered. Open means you got back some kind of response that says, hey, this port is open for business. So if it's a TCP SYN, it sends back a SYNAC. Closed, usually you'll get a response of reset. You send a SYN and the host sends back a reset saying this particular port is not open for business. If Nmap reports that the port is filtered, it means you had no response of any kind, which is actually for a TCP scan. That's really weird. You're supposed to get something back. If you get nothing, then it can't tell if it's open or closed or what, because something is blocking it. Either the host isn't up at the moment and not responding at all, or it's being blocked by a firewall or some router rules. Usually there will be no response, or there might be a destination unreachable. If you get a reported state of unfiltered, the port is accessible, but Nmap can't tell if it's open or closed. You'll get this in an ACK scan, which you will use to map firewall rules. Other scan types can then be used to identify is it open or closed. If you get open filtered, then Nmap is unable to determine the difference between open and filtered. The port is open but gives no response. No response could mean that the probe was dropped by a packet filter or that any response is blocked. If you see closed filtered, Nmap is unable to determine whether the port is closed or filtered, and you only see that in an IP ID idle scan. Now, one thing you can do when you're packet crafting is you can specify the source, or rather you can specify from the source what the route should be. Usually it's a router's job to determine the best path to send a packet on, but it is a rule of it. You can, as a sender, specify, I want this packet to go along a particular route following particular routers. That's called source routing. It's one of the options in the IP header field, so we can specify the source route. Usually an admin will disable that because I don't want you specifying sneaky ways around my firewall. So here's an example. I'm trying to get through the firewall. I can't to get to the destination, so I'll say source route. Go the sideways route to get past the firewall. Maybe this is coming in through a VPN to a VPN server or a dial-up server or something like that. So for specifying source routing, you can specify exactly which routers, which hops a packet must pass through. That's called strict source routing. Or some of the hops that a packet must pass through. That's loose source routing. Like I say, you specify it in the options field, and you can specify up to 9 hops. If you know that there's an alternate route, now maybe a router won't choose it because it's not the best route, but you know there's an alternate route that would let you go around the firewall, that's why you specify the source route, a dial-up connection or something that would ordinarily not be used. So here is, again, the IP header, and down here in the options, this is where we specify source routing, right here. We can see it's strict or loose, or we can record the route, or we put in a timestamp. So here's a Wireshark capture showing that. In this case, I'm saying an IP option, strict source routing, and I'm saying to get to this, we have to go through these hops. This is the next one, then the next one. Finally, to get to this destination. You can also manipulate the source port. So a stateless firewall might be configured to allow packets that appear to be from a server. So we'll say, hey, the source port is 80. It's coming from a web server. Sure, come on in. So we could Nmap pretending that it's coming from port 80, a web server. TAC-G is another way of specifying the source port. So maybe the firewall, if my source port is 242, well, the firewall's not going to let that come in. But if my source port pretends to be port 80, well, I'll go right on in. So that's a possibility. IP address decoys. Now, we've talked about generating decoys with Nmap. You're generating noise that you can hide amongst. You'll have multiple IP addresses that appear to simultaneously be scanning a target, so that the IDS or the sysadmin is trying to figure out who the real attacker is. You can explicitly specify these addresses or let the scanner randomly pick some. When we take a look at this is a firewall on a particular host. You see all of these things, and it's like, which one of these is the real attacker? They all appear to be scanning or attacking. We don't know which one's the real one. We can also spoof IPs when we want an intermediate machine to respond to a victim. We did that with the idle scan, didn't we? You can do it with all sorts of denial of service things. You craft a packet so the source is the victim's address. It's common in denial of service attacks. So imagine that you're sending all these ping packets out to all these different machines, and you're pretending that your true victim is the source. So all these machines will at once respond to this poor little victim, thinking they're responding, thinking that they're pinging back. They're doing an echo reply. So that denial of service is a very common use of IP address spoofing. Of course, we can also use it for firewall evasion as well. So here's our case where we're through the internet, we're sending a ping to all these what we call amplifiers, and they all respond back. They echo reply to our true victim. We can use timing. Now, I talked about timing. If you go really slowly, then a scan, or a ping, not a ping, but a SYN here and an ACK there, it'll just look like random noise to an IDS. It'll fall well below the threshold necessary to fire off an alert. You just make sure that the addresses and ports are targeted in random order. You don't want it pinging port 1, and then 2, then 3, because your IDS might recognize that pattern. Now, I will tell you this. Organizations now can have services, cloud services, that analyze all this traffic. Those cloud-based services are much better at identifying and spotting some of this evasion stuff, because they can recognize it over a larger period of time. And intrusion detection is usually only looking in small time slices, whereas cloud-based SIEM is looking in much bigger time slices. So your SIEM, the security event management system that notices these things, it might detect a very slow scan, whereas an IDS might not. Now, why would we probe a firewall? Well, we're trying to determine the firewall rule set. What ports are allowed? What ports are blocked? The firewall type, is it stateful or stateless? The weaknesses in the firewall's configuration. It's only going to be as good as the administrator's configuration. Any devices behind the firewall. We've talked about packet fragmentation before. We're going to split the probe packets into smaller fragments, send them to the target. The packet will be reassembled at the final destination. Hopefully, they're too small for the IDS or the firewall to recognize. The signature is just too short. They can't match it to a known malicious signature. IDSs are often configured to skip fragmented packets during scanning. We could use ACK scans or SYNFIN scans to map out firewall rule sets. Determine if a firewall is stateful or stateless. If you set both a SYN and a FIN bit at the same time, this would be a good way to bypass a rule that drops packets with only the SYN raised. Like the stateless firewalls, they're only checking one packet at a time. They're not keeping track of whole conversations, unlike a stateful. So they're looking for, incoming SYN flag raised, stop. But if it's something different, it might allow it through. You could use an ACK scan to determine if a firewall is stateful or stateless. Stateless firewall will be easier to get past than a stateful one. Stateless firewalls will block SYN packets based on port number. They're far less likely to block ACK packets because they'll think, oh, that's a response to an existing communication. So you can perform separate SYN and ACK scans against the same port. If the SYN shows some ports that are open and some closed, and the ACK shows all ports unfiltered, the firewall is likely either stateless or turned off. A stateful firewall will know from its table that is this ACK legitimate or not, because what a stateful firewall will do is it will track the handshake and everything. It'll notice, hey, you started on one port, you suddenly changed. Or you never completed a handshake. So it tracks every conversation in its state table. If an ACK scan shows some ports as filtered, it's likely a stateful firewall. Here's an ACK scan example. I am trying to scan this server in here, and I'm sending an ACK to destination 1207, 1208, 1209. I get no joy for these first two, but 1209 manages to make it through a packet filter, and the inside sends a reset back. I know that there's something back here, and now I know that it will respond. Now, true, it's not listening on port 1209, it sent me back a reset, but I know it's there. Here are some examples, SYN and ACK right here. So let's scan Windows 10 with Windows Defender Firewall off, with it dropped. Okay, so we're doing a SYN scan against a particular target. Fine. We come back and it shows 996 ports closed, 4 of them are open. All right, that's my SYN scan. Let me ACK the same address. And it shows all 1,000 scan ports are unfiltered. That means there's no firewall or it's stateless. A SYN scan returns 4 open ports, no firewall. Now, what if we turn the firewall on? Okay, I do a SYN scan again, and I can see that 999 of those ports did not respond. They were filtered. But I did get a response from one open port here. I do an ACK scan, and I see all 1,000 are filtered. That tells me it's stateful. Now compare that. If it says unfiltered, it's stateless, or it's turned off. If it's stateful, it says filtered. See the difference? That's how the ACK scan helps us. Now you might say, what's the point? Well, stateful firewalls are hard to get around. Stateless, they're only as good as the configuration put on them, and we might be able to take advantage of that. Now, in this day and age, built-in software firewalls like Windows Defender are going to be stateful for the most part. But there was a time when they were stateless, especially with Linux boxes. And stateless firewalls still have purpose because they have really good performance. Stateful, because they have to maintain state tables, the performance gets dragged down a bit. So when you have a device that needs super high performance, you might trade possible security for performance and use stateless, which you can do easily on a Linux box. Here's a scan against a CentOS Linux machine with the firewall turned off. We're doing a SYN scan, and it shows that all but 3 ports are closed. That's our SYN scan. We then do an ACK scan to the same thing. No firewall or stateless. The SYN scan returns 3 open ports. But if we do an ACK scan, then it says all 1,000 scan ports are unfiltered. Continuing with our scan of CentOS 7, we turn the firewall on right here. We do a SYN scan. It shows only TCP/22 SSH is being open. We do an ACK scan, and again it shows 999 filtered ports with only TCP/22 responding. This is a stateful firewall. Now, let's talk about scanning the firewall itself versus scanning past the firewall. If you have a firewall that's a separate appliance at the edge of your network, like a Cisco ASA or something like that, It by itself may have open ports on its IP address, unless the firewall is in transparent mode, then it doesn't have an IP address, but take a Cisco class for that. The firewall itself may have open ports for remote management. So it depends. Are you scanning the firewall's IP, or are you trying to scan something past the firewall? That will give us some information. If you port scan the firewall's front-facing IP, then you're going to see ports that the firewall itself uses. Now, of course, if the firewall is doing network address translation and is forwarding certain ports from the public address to a private address, like, I've got a private website inside, then the ports look like they're on the firewall itself. All it's doing is it's taking that and NAT translating and then sending it in. So a firewall that will NAT and port forward makes its ports look like they're on the firewall itself. It presents target ports as if they are its own ports, even though they forward them into the private network. To distinguish between a permitted port and the firewall's management port, try to open a browser to that port, banner grab the port, interrogate it with TAC-SCAP-V to see if you can get details about that port. Now, we've talked about the weirdo scans, null, fin, and Christmas. They're more stealthy than SYN. They can sneak past some stateless firewalls and some packet filtering routers. With the SYN bit off, they can go past rules that only look for SYN, or they can look for SYN raised, but the ACK flag set to 0, meaning we're beginning the conversation. But you will need to also TAC-SCAP-V to disambiguate or get more information to determine, is the port truly open or is it filtered. With a fin scan, we set only the fin bit. This, of course, breaks the rules of TCP. It should have an ACK. There will be an ACK raised on every single TCP segment ever in history, except the very first opening of the TCP handshake. Null scan also breaks the rules of TCP. You never have a TCP segment with no flags raised. Every flag or every packet is going to have something set. And then, of course, the Christmas scan is the illogical combination of fin, urge, and push all at once. Here will be the probe response. If you get no response received, even after retransmissions, Nmap will say, hey, this port is either open or filtered. If you get a TCP reset, port's closed. It's obvious. The thing told us it's closed. If you get an ICMP unreachable, type 3 code 1, 2, 3, 9, 10, or 13, it is filtered, and that is the firewall telling you that it's filtered. Now for UDP scans, UDP scan works by sending a UDP packet to every targeted port. For the most part, this will be empty, no payload, but for some of the more common ports, you could have a protocol-specific payload. Having a payload is more likely to get a response, because many UDP ports, unless you are actually asking it to do something, it won't do anything. Based on the response or the lack thereof, the port will be assigned one of 4 states. Any response from the target port, which is actually unusual if it's no payload, hey, it's open. No response, even after retransmissions, it's either open or filtered. ICMP port unreachable, type 3 code 3, port's closed. It's kind of like a reset, but only TCP does resets. Other ICMP unreachables, type 3 code 1, 2, 9, 10, or 13, filtered. UDP scanning very slow. Nmap has got to wait for each port to time out. And also, a Linux kernel will rate limit the ICMP destination unreachable messages to 1 per second, so it can slow down. So let's talk about UDP open filtered status. One of the big problems with UDP is that the open ports are rarely going to respond to empty probes, and I've already mentioned this. So the ports for which Nmap might have a protocol-specific payload, they're more likely to get a response, more likely to tell you truly if they're open or not. For the rest, we're going to simply pass an empty packet up to the listening application, which probably won't care, and will just say, what is this? It's an empty message? I'm not going to respond. If ports in all other states respond, then open ports could be deduced by elimination. Unfortunately, firewalls and filtering devices are also going to drop packets without responding. So if Nmap gets no response after several attempts, it cannot determine whether the port is open or filtered by our firewall. If we add service versioning to UDP scan, it helps to figure out more about that port. So like if we scan UDP version, it will help disambiguate the responses. And we're going to do this fast against scanme.nmap.org. And it says, yeah, we found one of them, UDP 53. So it is DNS. Now let's talk about something that's really kind of fun and interesting. It's a little archaic because you can only use it with packet filtering routers or stateless firewalls. And that's firewalking. It's used to determine exactly which device will permit or block a port. It's good for probing past a firewall into an internal network. We could even probe past a daisy chain of multiple firewalls. You can manipulate the time to live in a scan to distinguish between a protected server that has no port open, an intermediate firewall that blocks a port from being reached by the scanner. Firewall return an ICMP type 11 code 0 time exceeded if the port's allowed, the probe time to live expires, the probe is going to have to be sent to the live final target, and it doesn't matter if the final target is actually listening on the port. Nmap itself will report the port status as filtered. It's looking for a TCP response, not an ICMP response. A firewalker will notice the ICMP response and report the port as permitted. So what's happening is we're going to use time to live. Firewalking is almost like a trace route in some ways. You've got at least one firewall between us and a device on a whole other IP address. This is not a software firewall on the device itself. And the question is, can we port scan the firewall? And when we're port scanning it, if it allows a port, you're basically scanning a hole, which means you're going to get some kind of message here, but not because you got a response, but because the firewall will say, well, time exceeded because you just tried to scan a hole. So firewalking is really interesting. Here's an example here. I've got a firewall here, and this firewall has an FTP server behind it, okay? So I am going to try to send a TCP port 21 packet with a time to live of 1. It's scanning the hole. It's not trying to go any farther than the firewall, so the firewall will send back an ICMP expired in transit message because the packet expired at the firewall, which means the port's open. Which means the firewall will allow that port through. Now, whether there's anything behind it listening, I don't know. So here's an example. Nmap expects a TCP response. So here we are just go ahead and go. Don't try to do a discovery against port 21 with a time to live of 1, and just go for it. No host discovery. And we found that TCP21 filtered because we expected some kind of TCP response. The firewall actually returned an ICMP 11 code 0 time to live expired message right here. We go, that firewall is allowing TCP21 to go through it. Whether there's an FTP server behind it, I don't know yet, but I do know that hole exists. The ICMP error will include the original packet as the payload, so we can actually see the original packet here. There are automated firewalking tools. One of the challenges to firewalking is if you have multiple routers between you and the firewall you're scanning, they could interfere. So the first thing to do is figure out how many hops do we need to go through, because we have to preset the time to live to accommodate for those hops, right? Because firewalking is kind of like doing a tracert or a trace route. It manipulates time to live. So if there are a bunch of routers before we even get to the firewall, we need to increase the time to live to accommodate for those. So a firewalking tool, an automated tool, will assume there are multiple hops between the attacker and the firewall you're scanning. Now, they don't always work, just to let you know. Linux has a tool called Firewalk, and Nmap has a Firewalk script that will attempt to automate the firewalking process. So the first thing is a TCP-based trace route, what we call the ramp up. We're just trying to establish how many hops to the target. Once we know that, then we can increase the time to live so that, each hop is going to decrement the time to live. We want, by the time this packet gets to the router or the firewall, we want the time to live to just be 1 to see what the firewall does. So we'll keep on incrementing the time to live by 1 until all firewalls in the path are tested, because, okay, you have a bunch of routers up to this firewall. There could be another firewall behind it and another firewall behind it. So we're going to just keep on incrementing this until we have gone through all firewalls in the path. We'll either run out of hop count because you can only go to 255. That would be really weird. Or we actually get a response from a server that's way deep inside. The tool is searching for ICMP errors. Because of that, we don't actually have to reach the final destination. We're just testing firewalls here. If there are multiple packet filtering routers, firewalls in the path, then it will test all of them. Here's an example of the Linux Firewalk tool. So in this case, we're going to scan from 8079 to 8081. And we're going to send it out, Ethernet 0 interface, no name resolution. We're going to send TCP probes out. The firewall is 192.168.1.1, and the ultimate server that may or may not exist is 192.168.0.1. The response here is no response from 8079, so no response means firewall dropped it, disallowed. 8080 shows that 8080 is allowed. It's allowed. Now, the server might not use it, but at least the firewall allows it. And then no response for 8081, disallowed. Here's an example of the Nmap Firewalk script. So we don't specify a firewall, we just specify the target, the server that hosts the services. So we say, okay, we're going to script equals firewalk tac trace route to this final target here. We have a simple Nmap scan of the server which returns these results. This firewall is doing the filtering right here. We can see this is the firewall doing the filtering, blocking these specific ports. The filtering firewall in this case is the first hop to the destination. As we look through and as it gives us results, we can see hop 2, 6, and 7 are blocking certain ports. Router 2 is blocking TCP 21 to 2380 and UDP 21 to 23 and 80. Router 6, or firewall 6, packet filtering router, firewall, stateless firewall, is blocking TCP 67 and 68. And router 7, packet filtering router 7, is blocking TCP and UDP 25. Firewalking is really for stateless firewalls, although you can do some of it against stateful. So we have now seen firewall and IDS evasion. And now, on to the next topic. Let's do some advanced Nmap scanning. I have two VMs running. I have Kali Linux, and I've logged on as just the regular user Kali, and I opened a terminal. I also have Server 2016. I logged on as the administrator. The first thing I want to do is just double check the IP address of Server 2016. So we'll just go to Start, and we'll open a command prompt, and type ipconfig. Press Enter. Scroll back a little bit. Okay. 192.168.252.137. Going to Kali, can we ping that address? Ping 192.168.252.137. Yours, of course, is different. Press Enter, and yes, we're getting replies. Control-C, that's good. Now, let's go back to Server 2016, and let's raise the firewall. Let's turn it on, because the firewall is off, or at least mine is. So I'm just going to go to Start again, go to Control Panel. I'm in Large Icons view here. Go down to the Windows Firewall, click that. I can see that it's off for both the public and private profiles. I'm going to turn it on, and I'm going to turn it on for both profiles so I don't get messed up. Click OK. At this point, I don't really need to interact with Server 2016 anymore. We're just going to see what we can do. We're going to scan it using Nmap from Kali. I'm going to go over to Kali, and I'm going to clear. Enter. If you just type Nmap and you do a default 1000 most popular ports, and you're just a normal user like Kali, it will do a full scan, a full connect, a full TCP three-way handshake scan. You know what we're going to do, just to prove a point, we're going to launch Wireshark so we can double check what's going on. We'll just come up to Applications, and we should find it in Sniffing and Spoofing, and just launch Wireshark. Kind of big, let me resize it. Okay. And we're not doing anything on Bluetooth. I think we will work on Ethernet 0. Double-click it. Okay. It is starting to pick up stuff. Let's do just a default full connect scan here, and then we'll see what happens in Wireshark. So I'm just going to type nmap and just put in the target, 192.168.252.137. It's going to do a full handshake on the 1000 most popular ports. Press Enter. Give it just a moment. Oh, I can see some action going on already. Okay. It did find these ports open. Terrific. Let's come over to Wireshark and just take a look. Now you can see all this TCP here, and you can see that it's all coming from Kali, and it's going to Server 2016. And if we scroll over just a tad, we can see that it's trying SYN scans, but there's no SYN ACK just yet. It's trying to scan these popular ports in random order. And I see that it's even choosing random source ports as well. We could just scroll up to find SYN ACKs, but we could also do a display filter here. We just, up in the display filter, type TCP.ACK. You see that right there? TCP.ACK. Pick that, and then apply it. Go. That will find for us complete handshakes. See that? On some random client port, 44566 to port 80, I try the three-way handshake SYN, and then I'm also trying another one to 443. So 80 SYN, then notice that 80 is coming back with a SYN ACK, and then I do an ACK, and then I say reset, I'm not interested in talking any longer. So that would be just a normal, non-root scan. Let's try a SYN scan, where we don't even bother completing the handshake. There's no ACK. We'll just reset. So I'm going to start again. I'm not going to save. Continue without saving. And I'm going to take this filter off for right now. I'm going to come over to Kali, and I'm going to clear. And this time, because I'm not logged in as root, so I have to say sudo nmap type scan sin, small s cap s, and then the target, 192.168.252.137, hit it. The password for Kali is Kali, hit it. And now it's going, and we can see some red over here and some stuff happen. And of course we get the same ports that are open, but we did it differently. Let's stop. And let's apply the filter. We're looking for ACK. So this is tcp.ack. Let's just apply that. You can just either come way over here and click the little blue arrow, or you can just press enter. I'm going to press enter. So when I go down here, let me just scroll over a bit here. I see something right off the bat. I see a reset for 3389, which means that we did have a SYN-ACK. And if I look up a little bit, sure enough, here's me on port 37225, trying to go to the RDP port of my target, 3389, and I say SYN, and I'm trying some others real quick too. But then, just not too far down the line, 3389 comes back to me and says SYN-ACK. And I say, just kidding, reset. And let's see, do the same thing for port 110. Where do we see 110? Oh, there's the SYN for 110. There'd better be a SYN-ACK for 110. Yep, here's the SYN-ACK for 110, 110 coming back. And just kidding, reset. We also have 587 like that too. Do I see a SYN for 587? Oh, there it is. That's me going to the target's 587, SYN. And the target, 587 coming back to me, SYN-ACK. Just kidding. So that is a stealth scan, a SYN scan. Let's now try doing a fast scan. Now, it's fast not because we go faster, but because we just scan fewer ports. I think instead of the top 1,000, I think it's just the top 100. Let me clear this little filter. Let me start again. Continue without saving. And let me come over here to clear. And this time I'm going to nmap tac cap f and the target 192.168.252.137. Enter. It went quicker. It still found these open ports here, but it went faster because it didn't scan 1,000 ports, it scanned 100 ports. Let's come over to Wireshark Stop the Capture, and let's look for that SYN-ACK, tcp.ack, enter. Here is us to them on 60944. That's us using client port 60944, going to their 80. Now let me just scroll over so we can just see. Okay, here it is way at the top. Here's us on 60944 trying to start a handshake with 80 SYN. And 80 comes back to us with SYN-ACK. And we act back. And then we say, we're just kidding. So we didn't do this, the fast scan, we didn't do this as just a stealth fast scan. It was like a full connect fast scan. What if we were to do a stealth scan, a SYN scan, with the fast switch? We could try that. Let's clear this filter, start a new scan, don't save anything. Let's nmap tac ss tac f. See if we can do that. Target 192.168.252.137. Hit it. Oh, and it says you need root privilege. Know what we forgot to do? We forgot to say sudo. Okay, sudo nmap tac ss tac f 192.168.252.137. Hit it. Okay. And that was quite quick because it didn't even bother completing the handshake. Stop. Let's just search for ACKs real quick. Let's tcp.ack, press enter, and here's 80, where we, at 54298, do a SYN to their port 80. They come back to us with a SYN-ACK, and we say, haha, just kidding. So doing the SYN scan the stealth scan, the half-open scan, with the TAC-F fast was even quicker. All right. Now we could try some funky scans like a null scan or an ACK scan. These are things that we would test out a firewall with, and when we get to the firewall module, we'll play with that a whole bunch more. Why don't we try that? Let's just continue, and let's clear. Let's try a null scan. Let's sudo, because the null scan is going to require it. Nmap tac syn n for null, target 192.168.252.137, enter. We don't have to provide the Kali password this time because we just did it recently in this same session, same terminal. So it's going along and it's going through all 1,000 with null. So give it just a moment, and when it's done, we will take a look. Okay, all 1,000 scan ports are ignored. They're either open or they're filtered, but we get no response. We can stop here and we can just see. You'll see that we're sending to these ports, and we even redo some of these ports, but there's no response back. Let's just see what happens. Let's just peel open one of these. Double click it, and looking over here, just opening TCP, I can see if I scroll down here that I have no flags raised. Look at this. Expand this. No flags whatsoever raised. Now that is completely illegal, but sometimes you can pull that off with certain kinds of firewalls. All right, that didn't work so well, but we saw how it goes. What about if we were to do an ACK scan? Let's clear this filter. Everything is an ACK, just ACK. We're not trying to handshake, we're just ACKing. You know, the packet filtering firewalls, the ones that are just static, that are stateless, they'll think that, oh, an ACK flag is raised. That means you're in the middle of a session. Come on in. All right, let's just clear this. Let's sudo nmap tac scan a, ACK scan, and let's just do a fast one. We'll do a shorter number, just 100 of these, to 192.168.252.137, go. And it says, well, we scanned all 100 here, and they are ignored. So the firewall on Server 2016 doesn't fall for ACK scans. But you know, Windows firewalls these days are stateful anyway. So they would say, you never did a handshake, forget you. Let's come over here and stop the scan. And let's do a filter here for TCP. Oh, if we do ACK, they're all going to be ACK, right? They're all going to be ACK. Well, okay. But as we go along here, let me just scroll over. You can just see all ACKs. No sin, nothing. If we just pop one open, any of these, like 443, let's double click that one. And I'm just going to expand this a little bit better. CTCP, we're going to port 443. Scroll down a bit. The ACK flag is raised here. No others. Okay. How about if we do a Christmas scan? That would be a SX. All right, let's clear this. Let's start a new capture. Let's come over to Kali. Let's clear it. And let's sudo nmap tac SX. And let's make it fast. Tac F 192.168.252.137. Go. This one's going to definitely have some weird flags. And it says these are in an ignored state as well. Yeah, there aren't too many firewalls that fall for a Christmas scan anymore. Let's come over and stop the capture. And let's scroll over just a tad here. And look at this. These are all with fin, push, and urge raised. Let's just like open up one of these. Like I was trying to get to 1900, which is what? The UPnP, the Universal Plug and Play port. Let's double click and look at that one. Just kind of drag this down here. Look at the flags. Oh, how weird. Fin, push, urge. There's urge, push, and fin. You don't push something and say it's urgent and also try to stop your session at the same time. Too weird. All right. So that's those. Let's try some timing scans. Now I have to warn you, if we were to sudo nmap and we were to do a tact0, that's 5 minutes in between each port. I don't think we want to wait that long, even for just a few ports. So why don't we instead do, first of all, just the normal one. Now, tact3 is the default. That's normal. This will go at the same speed we're used to. So I'm just going to do the full 1,000 ports so we can see some differences. 192.168.252.137. We're looking at timing. Press enter. It will do the normal speed to go through all 1,000 ports. All right, just a few seconds. Now what if we went to the insane speed? T5. That's the fastest. In fact, that's so fast, it'll probably become unstable, but hey, I'm willing to try. Let's just up arrow here, and we're going to change it to 5. So, with a feel for how long normal is, how about insanely fast as it goes? Hit it. Yep, that was quicker. So that is using Nmap advanced scans. We'll come back to Nmap and do some even more crazy stuff when we study firewalls in the Firewall IDS and Honeypot module. Before you end this activity, be sure to go into Server 2016 and turn off the firewall for all profiles. Go into the control panel, go down to Windows Firewall, open that up, go to Turn Windows Firewall on or off, and turn it off on all profiles and click OK. And with that, we are ready to move on. Let's now talk about proxies. First of all, what is a proxy server? It's an intermediary device. It stands between the internal user and the internet, or the internet user and the internal resource. We use online proxies to hide our source address to avoid discovery. This increases privacy. We can do hacking anonymously, especially if you go through several proxies. We mask the source of an attack by impersonating a false source. We can remotely access intranets and website resources that are normally protected. The proxy is going to interrupt all requests sent by the user and reroute them to a different destination, making it see only the proxy server address. And we can chain multiple proxy servers to avoid detection. An edge proxy is what we traditionally thought of as a proxy. We would use it as a private organization. It sits at the edge of our network to protect our internal network from the outside world. A forward proxy fetches content from the internet and brings it back in. So a client wants to go out to an internet site. The proxy says, wait, I'll get it for you. It keeps the client session alive and starts a whole other session to the server on the internet. It goes and fetches the content, keeps a cached copy, and hands it to the client. And if another client wants a copy, it's got it handy. It doesn't have to go fetch it again. The downside of an edge proxy is that the content can become stale pretty quickly. In fact, I have a funny story where I had a website developer who was going through an edge proxy. She kept uploading content, and she was like, what? My content isn't updating. And I was like, oh, wait, I'm sorry. It is updating, but the proxy is fetching content from the website from 20 minutes ago. A reverse proxy works like an edge proxy, a forward proxy rather. It too is an edge proxy, but it works the other way. Incoming connections from the internet want content from our internal website. The reverse proxy says, just wait, I'll go get it for you. Just stand outside the front door. And then it goes and gets the internal content and hands it to the internet client. Here is an example. I've got a proxy here, and I've got an internal web server, and there's the internet. And people on the internet want to get web pages in our DMZ or whatever, but the proxy goes and fetches the content for them. So there's no direct communication between people on the internet and our protected web server. An anonymizer is what we think of these days as a proxy. This is a proxy on the internet. Now, this is for us, the hackers. It's created specifically so we can hide our true origin. Now, it may be free, it may be paid. The user will connect across the internet to the proxy server. The proxy will put the user on hold, and it'll start a whole separate connection to fetch the desired content and hands the content to the user. Since the proxy is the one actually doing the fetching, the web server sees the proxy's IP address as being the source. No one knows that the request is actually coming from a user, and the anonymizer is going to go and get it for the user. Well, the anonymizer knows it, but nobody else does. Because IP addresses are country-specific or region-specific, they can be blocked or tracked. But an anonymizer, if it's in a different country, using its own IP might not be blocked. It could be tracked, but only to the proxy, not to the end user. So let me give you a good example here. I was in Africa trying to get back to my bank in the United States, but my bank in the US saw, oh, this is an IP from Africa, block, because it thought it was some hacking attempt. So what I did was I went to an anonymizer in Europe, a country that was trusted, trusted more, I guess, and going through that proxy, I was able, no problem, to do my banking. Here are some use cases for using online proxies, anonymizers. We could surf anonymously, we could hack anonymously, we could bypass censorship or regional firewalls, we could evade surveillance or restrictions based on our IP. Anonymizers make it difficult for others to track you. Most anonymizers do not keep logs of their activity or their client connections. They do this on purpose. They want you to feel comfortable that no one can track you, no one can look at the logs. Anonymizers will typically be in a whole different legal jurisdiction, so they're not compelled to cooperate with your country's law enforcement. We can also use a variety of proxies in a daisy chain. We call this proxy chaining. And with proxy chaining, we'll have multiple proxies in series to fulfill the request. So we go to the first proxy, we get the request. The proxy goes to another proxy, and makes a request, which goes to a third proxy, etc., until finally the content is gotten, and then it's handed back to the first, or goes in reverse order. Handed back to this guy, who hands it to this guy, who hands it to this guy, who hands it to us. Proxy chaining makes it really hard to trace back to you, especially if these proxies are in different countries, different jurisdictions. You can use as many proxies in a chain as you want. Now realize, the more you have, the worse your performance is going to get, but you can use as many as you like. The more you use, the harder it's going to be to trace the activity back to you. There are a bunch of proxy tools. Proxy Switcher, Proxy Workbench, Tor, you've probably heard of Tor, we're going to talk about it in greater detail in a moment. CyberGhost, these are just a few. Additionally, you could use proxy tools that are not a whole separate server, but they intercept and allow you to manipulate traffic on your own machine, such as Burp Suite. Burp Suite will stand between your web browser and the web server, which allows you to check out the cookie, steal the cookie, manipulate values, that sort of thing. It's not a separate machine. It's an app that sits between your browser and the web server. There's also Charles and Fiddler, other types of internal proxy tools. These tools run on your own computer, as I said. And there are proxy clients like Proxifire and SoxChain. For mobile devices, there's ShadowSox, CyberGhost, HotShield, Netshield, lots more. You might want to also use a client app to manage your various proxy VPN connections, and Proxy Manager will do that. You could also create your own proxy using a tool called Servers Ultimate, and these are just some of the many. So how is a proxy different from a VPN, a virtual private network? With a VPN, your packets are encrypted and encapsulated. They're hidden, one packet inside of another. It's kind of like I'm going to hide stuff in the trunk of my car and throw a rug over it so you can't see it. But in this case, you're hiding a packet inside of a packet, and almost always you're encrypting. I mean, you can have VPNs where you don't encrypt, but that's for a networking class. Your client app on your computer or your phone will start the VPN. Your traffic will be encapsulated, hidden, and encrypted from the very beginning. You send your traffic to a VPN server on the internet in some other part of the world. That server then takes your traffic out of the VPN. So like, I'm going to start the VPN right here. And from here to a server in some other country, my traffic is encrypted. You can't even read what it is. That server will take it and take you out of the VPN. It will de-encapsulate, decrypt, and it will then send your packets on their merry way. It will look like it is the source. So it sends your unencrypted packets on the internet to their final destination. Your traffic will look like it came from the VPN server, not from you, actually. So here's an example. When I used that proxy, there was a VPN tunnel. So here's my bank in the USA. I'm out in an African nation here. So what I did was I used a VPN going to a proxy server in Belgium. And my bank didn't mind that, so I was able to do my banking. What are the components of a VPN? Well, you'll have a client app that runs on your computer or your phone. You'll have a server somewhere on the internet. That's going to be where your VPN ends and your unencrypted traffic keeps going. There will be a VPN protocol used to encapsulate and usually encrypt your data. Common protocols used today are IP security, IPsec, or Secure Socket Tunneling Protocol, SSTP, which basically uses TLS, HTTP. There's also OpenVPN, which is a TLS encrypted payload over TCP or UDP, but not using an HTTP transport protocol. There are legacy VPNs like L2TP and PPTP, but we don't use them too much anymore. So what is the difference between a proxy and a VPN? Well, VPN is one of the services of a proxy. VPN is an encrypted connection to a proxy. They will functionally accomplish the same thing. They're both used to hide your true origin. The mechanisms are different. The proxy itself is a server. You probably use a VPN to connect to it. In both cases, you secretly connect to the server on the internet. The proxy will fetch content on your behalf while you wait at home. If you are just going to a VPN server, which in most cases are going to be the same thing, proxy and VPN server, it decrypts your traffic and sends your unencrypted traffic to its final destination. Traditionally, proxies didn't use encryption. Your connection to the proxy and the proxy's connection on your behalf was traditionally unencrypted. Most anonymizers on the internet, however, use VPNs at least between you and them, and then the connection to wherever you're going will be clear text. So here is just a diagram showing proxy versus VPN. So here is us. We have a connection to a proxy, whether it's encrypted or not. The proxy keeps us on hold, keeps our session going, starts a whole new session, gets the content for us, hands it back to us. When we're using a VPN client, we have an encrypted tunneled connection where the stuff is hidden, packet inside of a packet and encrypted, to a VPN server, which then decrypts it and then sends it along its merry way to the destination. There are many online anonymizers, online VPNs, and typically these anonymizers have the VPN functionality. For additional privacy, you could increase the privacy settings in your browser for private or incognito browsing. You could clear cookies and history on your browser, or use a search engine like DuckDuckGo that does not track your history. Now, let's talk about Tor. The Onion Router. T-O-R, the Onion Router. This is a free and open source software for anonymous communication. It directs internet traffic through a worldwide, what we call overlay network. So the underlying infrastructure is the internet, but you have all these Tor routers, relays, over 6,000 of them, that are scattered all around. They'll conceal a user's location and usage from network surveillance and traffic analysis. Your route will change every 10 minutes with Tor. It makes it much more difficult to trace internet activity to a specific user. It's intended to protect personal privacy. However, it has become home to dark web criminal activity. Realize that Tor traffic is hiding in plain sight, but it's encrypted and going through all of these volunteer relays, so it's really hard to track. You're basically getting lost in a huge crowd of the internet. You need a Tor browser. It will aim to make all users look the same. It makes it hard to fingerprint you based on your browser or your device. It's actually very easy to set up and use. You can download the Tor browser from the Tor project, and then you can install it. It's actually quite simple. You just follow the wizard and you're done. Now, onion sites, these are website addresses that end in onion. So you hear about Tor, the Onion Router, onion sites. These are actually real sites, but you can't just get to them using a normal browser. You have to use a Tor browser because they're made to make everything look the same with a .onion extension. It's not a normal domain name. You can't access these with a normal web browser. You need a Tor browser. Addresses that end in .onion will point to Tor hidden services on the so-called deep web. Here's an example of Tor architecture. So here's me, and I am going to go query a directory authority for the nearest relay to me. So I will then connect to the first relay called the guard, and that relay will just forward my traffic through a network of Tor relays until we get to the exit point and I get to the actual destination. And this route changes every 10 minutes. That's why it's so hard to track. So how does Tor work? Alice, good old Bob and Alice, right? Alice's Tor client gets a list of Tor nodes from the directory server, and then it picks a random path to the destination. So the green links are the path, and this last bit here, getting to Bob, is in the clear. But her path will change constantly. So that is our look at proxies and all the little variations of proxies. And with that, we can go on to the next topic. So what are the countermeasures to scanning? Well, let's take a look. Start with port scanning. Put a software firewall on all devices, certainly the servers and any other device that'll take it. Limit the number of open ports, and I don't mean just on the firewall, well that's true, but also on the services that run on the device that have open ports. I mean, if this thing doesn't need an HTTP server, then turn it off. No? Block ICMP. Configure routers to disallow vulnerable features like source routing and IP fragments. Use intrusion detection to monitor traffic. And we have a whole module on that. Patch your hosts. Conduct your own port scans before the bad guys do. Ensure that intrusion detection routers, firewalls, all their firmware is updated. And if you have devices like IDS and firewalls that depend upon signature updates from the vendor, make sure that's updated regularly, as often as possible. Consider using a cloud-based service, a SIEM, Security Information Event Manager, to leverage the capabilities of cloud. Like a cloud-based SIEM, and of course it's not free, they're going to use more sophisticated analysis, artificial intelligence, longer-term analysis. See, your little IDS can only capture a small slice in time, but a SIEM can look over months and months and months. It can get trends from other case studies. It can use AI to recognize things that an IDS might not recognize. So if you're willing to spend the money, that's a really good way to go. In a high security environment, consider hard coding MAC addresses and IP addresses. That's hard work. For spoofing, do not rely upon IP-based authentication. Oh, you came from that IP? Sure, come on in. Digitally sign all transmissions. You can do that in the operating system. Use stateful firewalls with deep packet inspection and keep those updated. Disallow source routing. Oh, you came from my own network. Come on in. Not. Disallow incoming packets that appear to come from your own network. That's a spoofed source IP. Be cautious when you're allowing traffic based on a source port. Oh, you're port 80. You must be my web server that is getting some reply back. Okay, come on in. Hard code ARP entries where practical. Ooh, that's hard work. Hard code IP addresses where practical. Use switchport security. Take a Cisco class and you'll see how to do that. Configure your DNS server against cache pollution so that we can't inject some poisonous DNS entries. For banner grabbing, change the banner. Put a fake banner. Certainly have authorized users only. Don't say welcome in the banner. Early on in hacking history, there were hackers who won in court because they said, but the banner said welcome. I mean, it's not going to stop a hacker, but it will give you protection legally, okay? Especially do this for services that require users to log on. Turn off any unnecessary services. Hide file extensions from web pages, especially things that give away like ASPX or ASP. I see that in a URL, I know immediately it's a Microsoft IIS server. So you want to use services or use products that will hide that, will map it to something else. For your firewall, remember, your firewall is just the front door. And people can sneak around the front door. You need to have multi-layer defense. Not just a good firewall. You need to have defense all the way down to the data, the service, the operating system, the network, the physical environment, etc. Implement multiple firewall solutions. So one that's public-facing, one that's on the backside of the DMZ, one software firewall in every single host, every single server. Possibly one where a WAN link comes in from an untrusted site. Implement strong change management. Now, this is administrative, but it makes sure that you can see what changes are happening to your network. And you won't just turn your back and all of a sudden all these new things have been installed. You have no idea what they are. Stay on top of your patching and your updates. Set strong password policy. Use multi-factor authentication when you can help it. And look always for the ways around that firewall, those side doors, those back doors, the rogue Wi-Fi access points, or the legitimate Wi-Fi access points, the VPN and remote access servers, the private WAN links, or the VPNs to other sites, or the fact that people can physically move in and out carrying removable. And finally, regularly perform your own pen tests. So those are the countermeasures for scanning. Now let's move on. Let's review the key points of scanning networks. Scanning is part of active reconnaissance. When you scan, you're trying to discover possible targets, live hosts, open ports, protocols, services, operating systems, their versions, banners. Ping sweeps previously used ICMP echo requests to discover hosts, but now modern ping sweeps use ARP or some kind of TCP packets or some other protocol for host discovery. ICMP has numerous message types, and these message types, each of them may in turn contain code types. A port represents a process on the network. It's how we keep separate conversations separate. Both TCP and UDP use ports. Clients and servers, the client process, the server process, they'll each have their own port. And usually those ports are not the same. Services listen on well-known ports from 1 to 1023. Technically 0 to 1023, but we don't use 0. Services may request additional registered ports, and this is from 1024 to 49151 from their operating system. Clients will borrow dynamic ports from 41952 to 65535 from their operating system, and as soon as the client is closed, like the user closes the browser, that port number is given back to the operating system for it to reuse for something else. Please make sure you know these common ports. Let's go over them in excruciating detail. 21 FTP commands, 22 SSH, 23 Telnet, 25 SMTP, 53 DNS, TCP or UDP, 80 HTTP, 88 Kerberos, that's the authentication protocol for Active Directory, 110 POP3, 111 TCP or UDP, that is a Linux or Unix port mapper, which is the Linux or Unix functional equivalent of 135, the Microsoft Remote Procedure Call, RPC. 139, the legacy port for server message block, Microsoft's File and Print Protocol. 143, IMAP4. 161, UDP, SNMP. 162, UDP, SNMP traps, alerts. 389, LDAP. 443, HTTPS. 445, Microsoft Directory Service. We don't mean Active Directory, it's the logon port for an actual host. And then 3389, RDP. TCP uses a three-way handshake process, always started by a client, SYN, SYNAC, ACK. It's used to establish sequence numbers, starting sequence numbers, and to start a TCP session between client and server. And a client and a server can actually have multiple TCP sessions. TCP will also use a four-way goodbye handshake to end a session. FIN, ACK, FIN, ACK. We can abuse these things, right? A TCP SYN scan, also known as a stealth scan or half-open scan, does not complete the handshake, whereas a TCP connect scan, also known as a full scan or open scan, does complete the handshake. You can also scan raising various TCP flags to test a firewall, see how it will react. You can perform a UDP port scan, but there's no handshake involved, and you might not get any response from the target, especially if you send just an empty packet with no real request. Port scanning is the immediate prelude to vulnerability testing. Some scanning tools will do discovery, port scanning, and vulnerability scanning all in one comprehensive scan. Packet crafting manipulates TCP, UDP, and IP headers to probe open ports or to test firewalls or intrusion detection. Anonymizers or proxies will hide the source of a packet. You can use a VPN to encrypt your connection to a proxy. Creating a network diagram will give you an overview of the entire target network. It's useful in planning your attack. You can fingerprint an OS by examining its TCP or IP headers. You can banner grab to capture information about a network service or the operating system that it resides on. A list scan only performs DNS lookups. It doesn't actually scan the target. A zombie scan, also known as an idle scan, uses an intermediary machine to interact with the target. An FTP bounce scan uses a vulnerable FTP server to sort of forward commands. It will perform a scan against the real target on your behalf. You can perform SSDP scans to identify vulnerable home and small office networks. Nmap is the primary scanning tool used by hackers. ZenMap is a GUI version of Nmap for Windows, and it uses the same syntax. HPing, we're up to HPing version 3, can also perform scans and packet crafting, just like Nmap. You can use a number of tactics to evade firewall and IDS: source routing, fragmentation, source port manipulation, decoys, address spoofing, slow timing. Raising various TCP flags, like ACK or null or fin or the Christmas push urge fin, it's another way of possibly fake firewall or an IDS, really a firewall. Firewalking is the process of identifying which ports network firewalls will allow traffic through. And with firewalking, you can just see, okay, so many hops up to the front door firewall of that network. All right, what ports are allowed? And possibly there's another firewall behind it, and possibly another behind it, until we actually hit the host. And that is scanning networks. Now let's move on.